Sleep paralysis is one of the strangest and most misunderstood experiences a human being can have. In a single moment, the body is locked in silence, while the mind wakes into full awareness. The senses sharpen, but movement becomes impossible. Scientists have found that this frozen state between sleep and wakefulness can reveal some of the most fascinating secrets of the human brain. It is here, in this narrow borderland, that dreams can spill into reality, that ancient fears come alive in the dark, and that modern neuroscience meets the oldest stories of the night. Across the world, people have described seeing shadowy figures standing near the bed, hearing voices that whisper their names, or feeling a weight pressing down on their chest. For centuries, such experiences were attributed to demons, spirits, or alien visitors. Yet today, researchers know that these visions are the result of powerful biological mechanisms that govern the transition between rapid eye movement sleep and waking consciousness. Inside this mysterious state lies a scientific window into how the mind creates reality itself. Before we begin, I invite you to close your eyes, let your breathing slow down, and allow my voice to guide you on a peaceful journey through the world of sleep paralysis. Get ready to discover some of the most curious, surprising, and fascinating facts about this phenomenon, all told in a calm, soothing way, perfect for relaxing, learning, and drifting away. When you fall asleep, your body enters a complex cycle known as non-REM and REM sleep. During REM, the brain becomes almost as active as when you are awake. It is the stage in which most vivid dreams occur. To protect you from acting out those dreams, your brainstem sends inhibitory signals down the spinal cord, releasing neurotransmitters such as glycine and gamma-aminobutyric acid. These chemicals temporarily paralyze most skeletal muscles. The mechanism is called REM atonia. Normally, this atonia switches off as you wake. But sometimes, the timing misfires. Consciousness returns before muscle control does. You become awake inside a body that still belongs to the world of dreams. This is the core of sleep paralysis, a physiological mismatch between brain and body. The eyes may open, the room may appear exactly as it is, yet every attempt to move feels like pushing against an invisible wall. Breathing feels heavy because the chest muscles remain partially inhibited. The experience can last only a few seconds or stretch into minutes that feel endless. What makes sleep paralysis so fascinating to neuroscientists is how the brain fills that immobilized moment with imagery. During REM, the visual and emotional centers of the brain, the amygdala, hippocampus, and occipital cortex, are still active. The rational prefrontal cortex, however, remains partially offline. This imbalance allows dream imagery to merge with real sensory input. A coat hanging in the corner can morph into a human silhouette. A faint sound from outside may turn into a whisper inside the room. The brain's job is to interpret sensory data, and in this confused half state, it tries to explain the impossible sensation of being awake yet paralyzed. Throughout history, this same biological event has worn countless cultural masks. In medieval Europe, it was the incubus, a demon believed to sit on the chest of sleepers, stealing their breath. In Japan, it was called kanashibari, meaning bound in metal. In Newfoundland, Canada, people spoke of the old hag. The consistency of these descriptions across cultures has amazed anthropologists. Long before neuroscience, people in different corners of the world all described the same dark figure, the same crushing weight, the same immobility. Modern research suggests these visions are projections of the body's own panic response. When you cannot move and fear surges, the amygdala interprets that fear as an external threat, creating an image of danger to match the feeling. In controlled sleep laboratories, scientists have observed that heart rate and adrenaline levels spike during episodes. Brain scans show heightened activity in the temporal parietal junction, a region involved in sensing the body's position in space. This may explain why many people feel they are floating or even leaving their bodies during sleep paralysis. What they perceive as an out-of-body experience might be the brain's attempt to map a paralyzed body onto a vivid dream environment. Although frightening, sleep paralysis itself is not dangerous. It usually ends when the brain completes the transition out of REM and reactivates motor control. Some people experience it once in a lifetime. Others, especially those with disrupted sleep schedules, narcolepsy, or stress, may have it frequently. Lack of sleep, irregular bedtimes, jet lag, and sleeping on the back increase the likelihood. Genetic studies have even suggested that susceptibility may run in families, hinting at hereditary differences in REM regulation. One of the most intriguing aspects of sleep paralysis is the sense of presence, the unshakable feeling that someone or something is in the room. Cognitive scientists propose that this arises when the brain's body schema network becomes confused. Normally, you have an unconscious map of where your body ends and the outside world begins. During paralysis, that boundary blurs. The mind may externalize parts of its own awareness as an imagined figure standing nearby. Essentially, you sense yourself, but perceive it as another being. Interestingly, similar sensations can be triggered artificially. In 2007, neuroscientists at the École Polytechnique Fédérale de Lausanne used electrical stimulation on the temporoparietal junction of awake volunteers. The subjects reported feeling that someone was behind them, mimicking their movements, even though no one was there. This experiment provided striking evidence that the presence in sleep paralysis is a self-generated phenomenon rooted in specific brain circuits. Despite this, the emotional intensity remains real. Fear is amplified because the body cannot respond. The sympathetic nervous system floods the bloodstream with adrenaline, preparing for a fight or flight that never comes. The mismatch between readiness and immobility produces a loop of escalating dread. For some people, this fear transforms into vivid hallucinations, footsteps approaching, figures sitting on the chest, or even sensations of being dragged from the bed. These experiences, while terrifying, are purely the mind's creation, a product of REM imagery interacting with waking awareness. Yet, not all experiences of sleep paralysis are negative. A smaller group of people report feelings of euphoria, floating, or spiritual calm. Some describe luminous shapes, peaceful music, or sensations of unity. Researchers call this pleasant sleep paralysis. It may occur when fear is replaced by curiosity, allowing the experience to unfold without resistance. Studies suggest that people who practice lucid dreaming or meditation are more likely to interpret the episode as fascinating rather than frightening. The overlap between sleep paralysis and lucid dreaming is particularly compelling. Both occur at the boundary between REM and wakefulness, and both involve awareness within the dream state. In fact, some lucid dreamers intentionally induce sleep paralysis as a gateway to conscious dreaming. They allow their bodies to fall asleep while keeping their minds awake, then use imagery to step directly into a dream world. This delicate balance of consciousness has made sleep paralysis a subject of deep interest among neuroscientists studying metacognition, the ability to observe one's own mind in action. On a microscopic level, the phenomenon involves intricate communication between brainstem nuclei, the thalamus, and the cortex. The sublaterodorsal nucleus in the pons sends inhibitory signals that silence spinal, motor neurons. If this circuit remains active while the cortex reawakens, the body stays paralyzed. Neurotransmitters like acetylcholine keep the REM network active, while serotonin and norepinephrine, which normally rise during wakefulness, remain suppressed for a few moments. This chemical delay creates the perfect storm for sleep paralysis. Culturally, the fascination never faded. Artists, poets, and scientists have tried to capture its mystery. The famous 1781 painting The Nightmare by Henry Fuseli shows a sleeping woman pinned by a demonic creature, a powerful visual of the incubus myth inspired by the real sensations of paralysis. Modern filmmakers and writers continue to use it as a metaphor for helplessness, control, and the boundaries of consciousness. Clinically, understanding sleep paralysis helps researchers explore broader questions about the nature of awareness. It shows that consciousness is not a simple on-off switch, but a spectrum. The fact that we can be awake while the body sleeps, or dream while the eyes are open, challenges old definitions of what it means to be conscious. It suggests that the mind's perception of reality is a dynamic construction, and that construction can sometimes slip. People who experience frequent sleep paralysis often learn strategies to minimize it. Maintaining consistent sleep patterns, reducing caffeine, and managing stress all help. Sleeping on the side instead of the back lowers the chance of episodes. Some therapists use cognitive behavioral approaches to change how individuals interpret the sensations, turning panic into understanding. Education alone can reduce fear. When people know what is happening biologically, they often report that future episodes feel less threatening. In recent years, sleep researchers have developed detailed questionnaires, such as the Waterloo Unusual Sleep Experiences Scale, to measure the frequency and type of hallucinations people experience. Data from thousands of participants reveal recurring patterns: pressure on the chest, presence of a figure, floating sensations, occurring in more than 80% of reported cases. The consistency is remarkable. Despite cultural differences, human brains create nearly identical narratives when faced with the same neural conditions. From an evolutionary perspective, some scientists speculate that the paralysis mechanism may have developed to keep early humans safe during sleep. By preventing sudden movements, it would protect against falling from high resting places or alerting predators. The fear reaction, on the other hand, could have evolved as a rapid response system to perceived threats in the dark. What we experience as supernatural terror might therefore be an ancient survival reflex, misfiring in the modern brain. Still, mysteries remain. Why do some people sense benign presences, while others encounter horrific figures? Why do auditory hallucinations vary from soft humming to sharp screams? Neuroscience can describe the circuits, but subjective experience remains deeply personal. It is a reminder that consciousness, though studied in laboratories, is also a profoundly human and emotional phenomenon. Even now, new imaging technologies are providing clearer glimpses into the sleeping brain. Functional MRI and high-density EEG reveal that during sleep paralysis, the visual cortex lights up even with closed eyes. The line between inner and outer perception dissolves, creating a hybrid state in which imagination and reality overlap. This offers a living demonstration of how perception itself is constructed. how what we see is as much about our expectations as it is about the world before us. As you listen and breathe slowly, imagine how intricate these nightly transitions truly are. Billions of neurons synchronizing to maintain the rhythm between sleep and wakefulness. A single delay in that sequence gives rise to one of the most mysterious experiences known to science. Somewhere, right now, someone is awakening into that frozen moment, eyes open, but body still asleep, witnessing firsthand the strange frontier between the physical and the imagined. And just when they think they understand what is happening, something even more curious begins. A deeper layer of perception that challenges what it means to be awake at all. In that suspended instant between dreaming and waking, the mind does something extraordinary. It begins to search for meaning. When movement is impossible and fear fills the silence, the brain, shaped by millions of years of evolution, tries to make sense of the paralysis by building stories around it. These stories have followed humanity for as long as records exist. From the earliest civilizations to the digital age, every culture has looked into the darkness of the sleeping mind and found a reflection of its own beliefs, fears, and hopes. Ancient Mesopotamian tablets describe nocturnal demons called the Alu, being said to attack sleepers and press upon their chests. In the Greco-Roman world, physicians wrote of Ephialtes, a creature that leaps upon the sleeper, leaving them breathless and terrified. Medieval Europe personified the experience as the mare, a malevolent spirit that rides its victim at night. The very word nightmare still carries that origin. These accounts are remarkably consistent. Pressure, fear, immobility, and the sense of a nearby entity, long before the concept of REM sleep existed. Humans recognized the same physiological state and filled it with mythological detail. As medical science advanced, descriptions became less supernatural, but no less fascinated. 17th century physician IJsbrand van Diemerbroek documented cases of patients who awoke oppressed by a great weight, unable to cry out. In the 19th century, French neurologist Silas Weir-Mitchell coined the term night palsy. Each generation renamed the phenomenon, yet the experience itself remained unchanged. It was only in the 20th century, with the discovery of REM sleep by Aserinsky and Kleitman in 1953, that scientists finally linked these nocturnal visitations to measurable stages of brain activity. Modern researchers now recognize sleep paralysis as a manifestation of REM intrusion. When fragments of dreaming consciousness bleed into wakefulness, hallucinations occur that feel completely real. Using polysomnography, they can watch it happen, the eyes darting beneath closed lids, the body still, the electroencephalogram showing mixed frequencies that bridge sleep and alertness. What once seemed mystical is now reproducible in the lab, yet its emotional power remains untouched. Consider one of the most detailed modern case studies. In 1999, at a sleep clinic in Toronto, a 27-year-old graduate student volunteered for an overnight study. Electrodes recorded every flicker of her brain activity. At 4:17 a.m., her EEG suddenly shifted to a waking pattern, but her chin muscle sensors still showed complete atonia. Moments later, she pressed the panic button beside her bed. When researchers entered the room, she was fully conscious but could not move or speak. After the episode ended, she described feeling as if someone had entered the lab, leaning over her, radiating hostility. Her heart rate had spiked to 160 beats per minute. The data confirmed that she had been in REM sleep seconds earlier. The brain had woken, the body had not. Events like these reveal how little control we truly have over the timing of consciousness. They also show how profoundly our perceptions depend on brain chemistry. During REM sleep, acetylcholine surges while serotonin and norepinephrine plummet. This chemical environment enhances visual imagery and emotional intensity. When the waking mind intrudes, it interprets these dream-charged signals as external reality. The result is a hallucination experienced not as imagination but as fact. Psychologists studying fear conditioning note that the immobility itself magnifies panic. Normally, when we feel threatened, movement provides feedback of safety. We can run, fight, or at least flinch. In paralysis, that outlet vanishes. The amygdala fires alarm signals without resolution. Experiments show that even brief physical restraint can amplify fear responses in animals and humans alike. In sleep paralysis, the restraint is total, and the context, darkness, silence, solitude, makes the reaction even stronger. Cultural background shapes what the mind expects to see in that moment. In societies steeped in folklore about spirits or jinn, people may visualize exactly that. In technologically oriented cultures, the same sensations may be interpreted as alien abductions or intruders. Studies comparing populations in Egypt, Canada, Japan, and Denmark show that the content of hallucinations varies with belief systems. Yet the underlying physiology is identical. The phenomenon adapts to the language and symbols of each era. The experience can be so convincing that it has influenced major cultural movements. During the 1980s wave of alien abduction reports in North America, psychologists noted that many witnesses described waking in bed unable to move, sensing a presence, then seeing figures of light. When neurologists compared these narratives with sleep paralysis data, the overlap was striking. It did not diminish the sincerity of the witnesses. They truly experienced what they described, but it placed those encounters within a known neurophysiological framework. The same biological event, filtered through different expectations, can generate entirely different mythologies. Stress and lifestyle play significant roles in triggering episodes. Sleep deprivation lengthens REM periods and increases their intensity. Irregular schedules, such as those kept by shift workers or students, create ideal conditions for REM intrusion. Anxiety disorders and post-traumatic stress also correlate strongly with recurrent sleep paralysis, possibly because hypervigilant brains are more likely to regain partial awareness before the paralysis ends. Even simple factors like caffeine, nicotine, or heavy meals before bed can disrupt sleep architecture enough to provoke an episode. Yet there are mysteries still beyond explanation. Why do some people experience vivid auditory hallucinations, footsteps, knocks, growls, while others see nothing at all? Neuroimaging hints that auditory association areas may reactivate erratically during the transition. The mind, searching for coherence, translates random neural noise into recognizable sounds. In extreme cases, these can blend with dream fragments to create entire soundscapes. Some subjects report hearing their own names whispered clearly, even though no sound exists in the room. Sleep paralysis can also distort the sense of time. During episodes lasting less than a minute, individuals often report that several minutes have passed. This temporal stretching appears linked to disrupted activity in the parietal cortex, which contributes to time perception. In dreams, events unfold with fluid chronology. When that dream logic enters waking consciousness, the duration feels exaggerated. Although episodes often feel isolating, they are remarkably common. Surveys estimate that at least 1 in 5 people will experience sleep paralysis at some point in life, and roughly 5% have recurrent episodes. It affects all genders and cultures equally, often beginning in adolescence or early adulthood, the same period when RM density is highest. Even famous historical figures have recorded it. The composer Frédéric Chopin, scientist Nikola Tesla, and writer Guy de Maupassant all describe sensations identical to modern reports. For clinicians, distinguishing sleep paralysis from other disorders is essential. Narcolepsy, for instance, includes similar symptoms, but adds uncontrollable daytime sleep attacks and cataplexy, sudden muscle weakness triggered by emotion. In isolated sleep paralysis, daytime function remains normal. Misdiagnosis can lead to unnecessary medication or anxiety. Understanding the benign nature of the phenomenon often brings immediate relief to sufferers. When episodes become frequent, doctors sometimes prescribe brief courses of antidepressants that suppress REM sleep, reducing occurrences. However, behavioral approaches are preferred. Establishing consistent bedtime routines, avoiding screens before sleep, and creating a quiet, dark environment can greatly reduce the frequency. Breathing exercises and mindfulness practices help by lowering baseline anxiety. In cognitive therapy, patients learn to reinterpret sensations, recognizing the episode as temporary, focusing on controlled breathing, and waiting calmly until movement returns. One remarkable study from 2015 demonstrated how education transforms perception. Volunteers who received a 30-minute explanation of the biological mechanisms reported 50% less fear during subsequent episodes compared to those who received no explanation. Knowledge itself rewired the emotional response. The brain, understanding that paralysis is temporary, no longer triggered the same level of panic. Beyond individual relief, researchers see sleep paralysis as a window into the construction of consciousness. It shows that perception, emotion, and motor control are interdependent systems that can become unsynchronized. This temporary disconnection reveals the scaffolding of awareness, the machinery usually hidden behind seamless experience. Neuroscientist Balan Jalal describes it as a natural experiment created by the brain itself, offering clues to how waking reality is built and maintained. Some scientists go further, suggesting that studying sleep paralysis could help explain near-death experiences, lucid dreams, and other boundary states. In all of them, the brain blends internal imagery with external perception, while the body remains still. The similarity hints at a shared underlying process, the brain constructing a model of the world while detached from direct physical feedback. The emotional dimension of the phenomenon cannot be overstated. People often describe the first episode as life-changing, not only because of fear, but because of its sheer realism. The vision of a presence, the pressure on the chest, the certainty that something profound just occurred. These impressions linger for years. For some, it becomes a source of artistic inspiration. Writers have turned their experiences into novels, filmmakers into psychological thrillers, and musicians into haunting compositions that capture the feeling of immobility and awe. Cultural researchers trace these creative echoes across centuries. The Icelandic sagas mention Mara Press, the witch's crushing ride. Inuit traditions tell of shamans who enter paralyzed trances to communicate with spirits. West African folklore speaks of Ogun Oru, the nocturnal pressing spirit. Each narrative reveals how humans transform physiological events into cultural meaning. Even in societies with advanced neuroscience, the emotional language of haunting persists. perhaps because it expresses something beyond data, the primal vulnerability of being conscious yet powerless. The phenomenon has also been used as evidence for supernatural belief systems. In communities where faith and daily life intertwine, sleep paralysis can be interpreted as a spiritual test or an encounter from beyond. Anthropologists note that these interpretations, while differing in content, often serve similar psychological functions. They provide context, comfort, and a sense of control. Knowing why something happens, whether the explanation is scientific or spiritual, reduces distress. Understanding brings peace. From a strictly physiological standpoint, there are rare variants worth mentioning. Some individuals experience complex sleep paralysis, where the episode repeats multiple times in a single night. Others report hypnopompic chaining, brief cycles of paralysis separated by seconds of mobility, suggesting unstable boundaries between REM and wakefulness. These patterns are studied to understand how sleep stages overlap and how the brain resets itself after partial arousals. Research into genetics is uncovering intriguing clues. Twin studies show higher concordance rates in identical twins compared to fraternal ones, implying hereditary factors. Specific gene variants related to circadian rhythm and neurotransmitter regulation may increase susceptibility. The goal is not to pathologize the condition, but to map how different brains handle the transitions of consciousness. Technological progress now allows researchers to capture real-time brain imaging during spontaneous episodes. Portable EEG caps combined with high-speed infrared cameras record muscle tone, eye movement, and facial microexpressions. These tools reveal that during paralysis, microtremors occasionally appear in the face and fingertips, suggesting partial activation of motor neurons. Such details refine our understanding of how the brain gradually releases the body from atonia. While laboratories decode the biology, the human experience remains at the center. Many who once feared sleep paralysis come to view it with curiosity. Online communities share coping techniques and even artistic interpretations. People exchange stories of confronting their visions, speaking calmly to the imagined presence, and watching it dissolve. The simple act of acceptance often ends the episode sooner, highlighting the powerful link between emotion and perception. Among long-term experiencers, a surprising number describe eventual comfort with the state. Some use it as an entry point for lucid dreaming or meditation. They report that by focusing on breathing and imagining movement, rather than struggling physically, they can shift smoothly into a dream landscape. This voluntary use of paralysis as a bridge between worlds blurs the boundary between science and subjective exploration. For neuroscientists, these accounts demonstrate the brain's adaptability. A state once defined by fear can become a tool for introspection. It shows that perception is not fixed, but guided by interpretation. Change the narrative, and the experience itself changes. As the night deepens, and countless sleepers around the world drift through the stages of REM, some will awaken into that strange halfway space. Their hearts will race, their minds will search for meaning, and the same ancient drama will unfold again. A drama written not by ghosts or demons, but by the living brain. And in that moment, just as the darkness seems to press closer, another layer of mystery begins to reveal itself. A question that reaches beyond biology, touching the edges of consciousness itself. When scientists speak about consciousness, they often compare it to light, filtering through layers of atmosphere. Each layer bends, colors, and softens the beam until it reaches the ground of awareness that we call waking life. Sleep paralysis occupies one of the thinnest of those layers. Here, the beam has not yet cleared the clouds. Traces of dreaming still scatter across the mind. Studying this fragile condition has given researchers extraordinary insights into how perception is built and how easily it can be fooled. During a typical night, the brain cycles through stages lasting about 90 minutes. Non-REM sleep dominates the early cycles. REM becomes longer toward morning. Consciousness normally fades completely during deep sleep, but micro-awakenings, brief sparks of awareness lasting seconds, occur naturally. Sleep paralysis represents an extended micro-awakening in which the cortex re-engages before the brainstem withdraws its chemical blockade on movement. That small reversal turns an invisible neural process into a vivid human event. Inside the laboratory, this sequence can sometimes be observed in real time. At the University of Montreal, researchers monitoring subjects prone to recurrent paralysis noticed a characteristic pattern, a burst of alpha waves, then a sudden desynchronization across frontal and temporal lobes. Within seconds, heart rate increases and galvanic skin response spikes, reflecting fear. The subject's eyes flick rapidly under closed lids, and the EEG shows mixed frequencies that resemble both REM and wake. This coexistence is called dissociated sleep. It is, in essence, two states occupying the same brain. The dissociation explains many of the phenomenon's features. The dream-generating limbic system continues to create imagery. The sensory cortices receive real input from the external environment. The two data streams overlap, and the mind interprets them as a single reality. That is why a shadow on the wall can seem alive. Why? Footsteps sound purposeful. Why light sources appear to shimmer with intention. The brain is combining external photons and internal imagination into one coherent, emotionally charged world. Modern cognitive neuroscience has mapped parts of this fusion process. The fusiform gyrus, responsible for face recognition, activates strongly during hallucinated presences. Even a faint pattern resembling eyes or a nose is enough to trigger it. Once engaged, it projects the perception of a living being. Meanwhile, the amygdala amplifies the emotion associated with that perception, and the anterior cingulate cortex attempts to evaluate threat. Within seconds, a coat on a chair becomes a figure. Adrenaline floods the body, and the narrative of danger takes form. The sense of pressure on the chest, perhaps the most universal symptom, arises from simple mechanics combined with interpretation. During REM, breathing becomes shallow and relies more on the diaphragm than on intercostal muscles, which remain partially inhibited. Lying on one's back exaggerates the feeling of weight. When panic sets in, the subjective experience becomes suffocation, and the brain invents a cause, a force pressing down. What feels supernatural is a physiological chain of muscle tone, posture, and emotion. Yet, understanding the mechanism does not erase its emotional impact. In 2018, neuroscientists invited recurrent experiencers to describe the moment when fear begins. Nearly all said it started the instant they realized they could not move. Awareness itself, more than the hallucination, triggers terror. The inability to act violates one of the deepest assumptions of consciousness. That intention leads to movement. When that link breaks, the self momentarily loses agency. Philosophers studying free will find this fascinating. The event is a natural experiment showing that the feeling of control is built from predictive brain models, not from movement itself. These insights align with predictive processing theory, which proposes that the brain constantly forecasts sensory input and updates its model when errors occur. During paralysis, motor predictions, "I will move my arm," fail to produce expected feedback. The resulting prediction error cascades through cortical networks, generating vivid explanations, "Something is holding me down." Thus, hallucination becomes a logical attempt to reduce error within the brain's internal model. What feels like horror is the machinery of prediction correcting itself. Experiments with lucid dreamers shed even more light on this process. Experienced lucid subjects can signal researchers from inside dreams by performing agreed-upon eye movement codes. Left, right, left, for example. In some sessions, participants intentionally entered paralysis before transitioning to full lucidity. Brain recordings during those transitions revealed smooth increases in frontal lobe coherence, suggesting that meta-awareness, knowing that one is dreaming, emerges as frontal circuits regain communication with sensory areas. These moments blur any clear border between sleeping and waking. Consciousness becomes a continuum rather than a toggle. The implications reach far beyond sleep research. They suggest that the brain can host multiple simultaneous realities, one generated by external stimuli, another by internal simulation. During normal waking life, the two align closely, creating a stable world. In sleep paralysis, alignment slips, and the mind witnesses the split directly. For philosophers of mind, this state provides empirical evidence that perception is a controlled hallucination constantly tuned by sensory input. Memory studies deepen the intrigue. When volunteers recall episodes, they often describe them in extraordinary detail, yet objective timing shows distortions. Emotional memory consolidates more strongly than neutral memory, so the fear component becomes dominant. Neuroimaging after episodes shows heightened activity in the amygdala and hippocampus for hours, explaining why the memory feels etched. Interestingly, positive reinterpretation, such as understanding the event scientifically, reduces later amygdala reactivation. Education literally rewrites the emotional tag attached to the memory. Some laboratories now use virtual reality setups to simulate aspects of sleep paralysis safely. Participants lie still while immersive projections restrict perceived movement and introduce subtle visual figures. Physiological monitoring confirms that similar fear and presence sensations arise, though weaker. These experiments allow researchers to test interventions, rhythmic breathing audio, guided narration, or tactile cues that restore agency. Findings show that when a calm voice reminds participants of safety and transience, the sense of oppression diminishes rapidly. The brain's interpretation can be steered by reassurance. Environmental factors play their own role. Room temperature, light level, and background noise influence the threshold between REM and wake. Slight warmth promotes vivid dreaming. Sudden cooling increases microarousals. Nocturnal sounds, traffic, wind, a refrigerator hum, can blend into hallucinated auditory content. Sleep scientists therefore design study rooms with neutral acoustic profiles to minimize accidental triggers. In everyday life, maintaining a consistent, quiet environment serves the same function. Hormonal rhythms intersect with these patterns too. Cortisol, the body's primary stress hormone, begins rising in the early morning hours, preparing for wakefulness. Episodes frequently occur at that time, when REM is intense and cortisol peaks. Elevated cortisol may enhance alertness before muscle tone returns, nudging the mind into awareness prematurely. This biochemical coincidence might explain why many episodes happen just before dawn, accompanied by faint light entering the room. The perfect stage for confusion between dream and reality. In rare clinical documentation, Scientists have recorded subjects describing dual vision, seeing both the real room and dream imagery simultaneously. High-resolution EEG shows alternating bursts of alpha and theta waves during those moments, suggesting oscillation between external and internal attention. It is as if the brain flips frames of two movies in rapid succession, creating a translucent overlap. The experience, described as seeing through two worlds, underscores how flexible perception can be. Beyond physiology, researchers explore personality correlations. People with high imaginative capacity, creativity, and absorption scores experience more vivid paralysis imagery. These traits overlap with openness in the 5-factor personality model. Rather than being pathology, they indicate a brain more sensitive to sensory imaginative blending. This may explain why artists, writers, and musicians throughout history have described recurring paralysis that later inspired their work. The brain that easily enters liminal states may also access richer creative associations. Cross-disciplinary teams now use magnetoencephalography to measure millisecond-level activity during transitions. Early findings reveal that thalamic relay stations oscillate irregularly just before episodes, briefly allowing dream signals to reach sensory cortex while suppressing motor output. Understanding this timing could one day lead to targeted therapies. Gentle electrical or acoustic stimulation precisely synchronized to help the brain exit paralysis smoothly. For those who live with frequent episodes, community support is powerful. Online networks offer spaces to share accounts without judgment. Reading hundreds of similar stories normalizes the experience and reduces fear. Psychologists note that collective narrative transforms private terror into shared curiosity, turning a disorder into data. It demonstrates a universal pattern of the human mind, confronting the unknown and finding meaning through communication. Among recorded testimonies, one theme recurs: the moment when fear gives way to observation. Individuals who manage to remain calm often report extraordinary clarity. Sounds sharpen, colors intensify, and a profound stillness fills the room. Some compare it to meditation, others call it the most vivid consciousness they have ever felt. Measurements show slightly elevated gamma wave activity in such episodes, the same frequency band associated with focused attention in experienced meditators. This suggests that the mind, when unthreatened, can use paralysis to access an unusually coherent state of awareness. In recent conferences, neuroscientists discuss whether this heightened clarity could serve scientific study itself. Volunteers capable of remaining conscious in paralysis might become ideal subjects for observing transitions between neural states. They are, in effect, explorers of their own brains. Researchers already collaborate with lucid dreamers to map sensory boundaries. Similar work with paralysis experiencers could reveal how self-awareness arises and dissolves. Every discovery, however, raises new questions. Why does the mind sometimes project benevolent figures instead of frightening ones? Could emotional expectation before sleep influence imagery selection? Small trials where participants visualize protective or calming scenes before bed show modest reductions in negative hallucinations. Conditioning the imagination appears to guide what content emerges when REM intrudes. The brain may choose from emotional templates stored in memory, aligning the vision with the sleeper's mood. These insights merge neuroscience with psychology in a way that respects both biology and subjective meaning. The phenomenon is neither purely mechanical nor purely mystical. It is a dialogue between neurons and narrative. Understanding this dialogue requires humility, acknowledging that even with instruments and data, we are still interpreting experiences from the inside out. The next frontier lies in decoding how consciousness reintegrates after paralysis ends. EEG data show a distinct rebound pattern. As motor tone returns, frontal parietal networks synchronize rapidly and emotional centers quiet. Many subjects describe a brief afterglow, a sense of relief mixed with wonder. Heart rate slows, breathing deepens, and the world feels newly tangible. This re-entry may teach us as much about waking consciousness as the episode itself, for it reveals how stability is restored after chaos. As night progresses toward dawn, these transitions repeat silently in bedrooms across the planet. Most sleepers never notice them. A few awaken inside the machinery and witness it working. They become accidental scientists of their own minds, recording sensations that textbooks later explain. And each time, as the paralysis fades, a lingering question remains, one that neuroscience has not yet answered. If awareness can exist without movement, without external input, suspended between dream and waking, then where exactly does consciousness live? In laboratories lit only by the glow of monitors. Researchers continue to watch the sleeping brain flicker between worlds. Electrodes record storms of microscopic electricity, while cameras capture the stillness of the body. Each night's data adds another fragment to a puzzle that spans medicine, psychology, and philosophy. The more scientists learn, the more they realize that sleep paralysis is not an error of biology, but a window into how consciousness is assembled. When an episode ends, the first twitch of a finger signals that motor neurons have finally broken free from inhibition. The neurotransmitters serotonin and norepinephrine surge upward, restoring tone to muscles that have been silent. Within seconds, posture control returns, heart rate normalizes, and the rational cortex reasserts order. Yet for the person who has just experienced it, the after image lingers, the echo of a presence, the weight that felt impossibly real. Interviews show that even people who fully understand the physiology often sit in bed afterward, heart pounding, trying to decide which sensations belong to the body and which to the mind. The distinction between those two domains may be less rigid than we imagine. Functional imaging reveals that during paralysis, sensory cortices respond to imagined stimuli almost as strongly as to real ones. The same neural networks that process touch, sight, and sound can be activated from within. In effect, the brain can generate reality internally with nearly the same fidelity as external input. This discovery reaches far beyond sleep research. It touches virtual reality technology, trauma therapy, and even pain management, where controlled imagery is used to alter perception. To neuroscientists, sleep paralysis demonstrates that perception is an active construction. The brain does not simply receive data, it predicts, fills gaps, and edits information to maintain a coherent story. When that editing process falters, we glimpse the raw mechanics of consciousness itself. This is why so many who study the phenomenon describe it not as pathology, but as revelation. A moment when the curtain lifts and we see how experience is made. Across the world, cross-cultural studies continue to map its prevalence. In sub-Saharan Africa, nearly 44% of participants in recent surveys reported at least one episode. In Japan, the rate hovers near 30%. In Britain and North America, between 20 and 25. These numbers translate into hundreds of millions of people who, at least once, have awakened unable to move. That universality unites humanity more than it divides. Whether a person calls the sensation kinashibari, old hag, jinn attack, or simply sleep paralysis, the underlying biology is the same. The brain's delicate transition misaligned by fractions of a second. Clinicians now use this knowledge to reassure patients who once feared supernatural causes. Simple explanations. Your body is still in REM, but your mind is woken. Reduce anxiety dramatically. In clinics in Cairo, Kuala Lumpur, and London alike, education sessions lower symptom severity more effectively than medication alone. The message is consistent. Understanding transforms terror into observation. Preventive measures follow predictable logic. Regular sleep schedules stabilize circadian rhythms. Side sleeping lessens chest pressure. Moderate exercise improves overall sleep quality. Avoiding stimulants and heavy meals before bed reduces REM fragmentation. Though these recommendations sound ordinary, they address the precise biological triggers that turn ordinary REM transitions into paralysis. Consistency is the quiet antidote. Meanwhile, cognitive scientists ask deeper questions. Why does awareness sometimes emerge during paralysis at all? Theories point to the ascending reticular activating system, the brainstem network responsible for arousal. Slight fluctuations in its firing rate may awaken the cortex prematurely. Genetic differences in these neuron sensitivity could explain why some individuals are prone to partial arousals. Mapping these circuits might eventually allow medicine to predict who is susceptible, not to stigmatize, but to personalize sleep health advice. Other studies focus on the relationship between paralysis and creativity. In questionnaires given to artists, writers, and engineers, those reporting frequent episodes also scored higher on divergent thinking tests. The same openness that allows the mind to merge dream and reality may facilitate innovation in waking life. The link is correlation, not destiny. Yet it suggests that the neural flexibility producing vivid imagery in sleep may also generate originality in art and science. Technology now allows unprecedented observation of these states. High-density EEG helmets, wearable heart rate sensors, and infrared eye trackers collect gigabytes of data nightly. Artificial intelligence algorithms analyze patterns invisible to human observers, finding subtle markers that predict paralysis minutes before it begins. One experimental device plays a gentle audio tone when those markers appear, nudging the brain fully awake before atonia becomes conscious. Early trials show promise, hinting that a future of personalized preventive sleep medicine may be near. But even as solutions emerge, curiosity deepens. Philosophers of mind and theologians alike ponder what the phenomenon reveals about the human condition. It demonstrates that awareness can exist independent of motion, that perception can arise without external stimuli, and that fear can create substance where none exists. It invites humility, the realization that our sense of reality depends on fragile biological timing. Some researchers now collaborate with meditation practitioners to explore similarities between paralysis and deep contemplative states. In both, muscle activity drops, breathing slows, and awareness turns inward. EEG comparisons show overlapping frequencies in the theta, low alpha bands. The difference lies in control. Monks and experienced meditators enter immobility intentionally. With calm, paralysis arrives unbidden. Understanding why the emotional outcome diverges could guide therapeutic approaches that teach voluntary calm during involuntary stillness. There is also growing interest in the moral and existential dimension. To experience sleep paralysis is to confront vulnerability. In that moment, stripped of movement and speech, a person meets the limits of self-control. Some emerge from it with newfound empathy for those who live with physical paralysis. Others describe a deeper appreciation for ordinary wakefulness. What begins as fear often ends as insight. Recent longitudinal studies track how perception of the phenomenon evolves over years. Initially, 80% of participants label it frightening. After education and experience, the proportion reverses. Most later episodes are described as neutral or even fascinating. This transformation demonstrates the brain's capacity to recontextualize identical sensory events through meaning. Interpretation, not sensation, defines emotion. The phenomenon also illuminates how easily the brain accepts impossible experiences. During paralysis, people often feel touched, hear speech, or see figures, yet post-episode skepticism rarely erases the memory's realism. This resilience shows that belief and sensory certainty are intertwined at deep neural levels. Understanding this relationship helps psychologists address hallucinations in other contexts, from grief visions to psychosis, without dismissing the validity of subjective experience. Sleep paralysis research has therefore become a multidisciplinary bridge. Neurologists study its circuits, psychologists its emotions, anthropologists its myths, and philosophers its implications for consciousness. Each discipline contributes a layer of comprehension. Together they form a picture both biological and profoundly human. At the same time, caution guides the field. Scientists emphasize that the goal is not to strip mystery from experience, but to ground it. Explaining the mechanism does not negate the awe it inspires. For many who study or endure it, sleep paralysis remains one of the most convincing demonstrations that the mind can manufacture an entire reality with sensory precision. Recognizing that power evokes wonder, not dismissal. Future directions include using transcranial magnetic stimulation to modulate brainstem cortex communication, developing non-invasive therapies for chronic sufferers, and integrating virtual reality training that teaches recognition and calm. Each experiment adds a piece to our understanding of how consciousness stabilizes every morning when we wake. And still, each night, millions slip silently into the same unknown. Somewhere a student studies late, finally falls asleep, and wakes moments later to find the body frozen. Somewhere else, a shift worker drifts into REM during an afternoon nap and opens their eyes into a half-dreamed world. Every instance is a natural reminder of how thin the boundary truly is between awareness and oblivion. As dawn approaches, the global chorus of sleepers begins to stir. Those who have experienced paralysis will remember fragments: the hum of the room, the figure at the door, the sudden release. Most will rise, breathe, and continue their day, never realizing that their brief ordeal mirrors patterns unfolding in brains across continents. The phenomenon connects us in shared vulnerability, a collective whisper from the border of consciousness. Dreaming is the other half of the equation that makes sleep paralysis possible. If paralysis is the stage mechanism, dreams are the performance itself, an internal theater where perception, emotion, and memory combine to rehearse reality. Understanding this nightly production reveals why the border between dream and wake can blur so easily. For decades, scientists believed dreams were random byproducts of neural activity. In the early 1970s, the activation synthesis model proposed that the brainstem fired bursts of electrical noise during RMN, and the cortex simply tried to make sense of it. Yet modern imaging paints a more intricate picture. Dreams are not meaningless static, They are simulations built from fragments of experience, guided by emotion and memory. The same circuits that process learning and creativity are active within them. Functional MRI shows that during REM sleep, the limbic system, especially the amygdala and hippocampus, lights up dramatically, while the dorsolateral prefrontal cortex, seat of logic and self-critique, quiets. This combination allows intense emotion without rational censorship. It explains why dreams can feel both absurd and deeply significant at once. The mind is free to test associations without the constraints of waking reason. In this chemically altered state, acetylcholine dominates, dopamine fluctuates unpredictably, and norepinephrine nearly vanishes. The absence of norepinephrine, which normally dampens emotion, lets feelings surge unfiltered. That chemical landscape is also ideal for consolidating memories. The hippocampus replays recent experiences, weaving them into long-term storage. Every night, the brain edits the day's footage, splicing lessons and sensations into the larger film of self. Dream content mirrors this process. People who study new skills often dream of them. Musicians replay melodies, athletes rehearse movements. When researchers taught participants a maze task, those who dreamed about it improved twice as fast. The dreaming brain, though detached from physical movement, strengthens neural pathways as if practicing in secret. Yet, dreams are not mere replays. They remix. Neural networks draw fragments from different contexts, producing combinations the waking mind might never invent. This is why dream imagery often inspires creativity. The chemist Kekule saw the structure of benzene as a snake biting its tail. Paul McCartney heard the melody of yesterday in a dream. What begins as random recombination can become innovation when consciousness later interprets it. The border between dreaming and wakefulness grows even more fascinating in lucid dreams. Those rare moments when a sleeper realizes they are dreaming. Around 55% of people experience at least one lucid dream in their lives, though only about 20% have them regularly. During lucidity, frontal brain areas partially reactivate, restoring self-reflection, while the rest of the brain remains in REM. This hybrid state resembles the awareness of sleep paralysis, but without immobility. In the laboratory, lucid dreamers have communicated with researchers by performing pre-agreed eye movement signals. These experiments confirm that consciousness within dreams can follow instructions, solve math problems, and even perceive external sounds. It means that part of the mind remains tethered to reality while immersed in an invented world. Studying this state offers clues to metacognition, the ability to think about thinking. Inducing lucidity deliberately involves similar techniques to those used by those exploring sleep paralysis safely, maintaining awareness as the body falls asleep, keeping attention on breathing or visualization. The key difference is emotional tone. Where fear locks the dreamer into paralysis, curiosity opens the door to lucidity. The same threshold crossed in panic becomes, under calm observation, a portal to conscious dreaming. Within lucid dreams, sensory realism can rival waking life. fMRI data show vivid activation of visual cortices and somatosensory areas. Dreamers report texture, temperature, even pain. Because the body is paralyzed, these sensations originate entirely in neural simulation. They demonstrate how the brain's model of the world can operate without physical input. The same principle underlying hallucinations and paralysis, but now controlled and benign. Researchers now study lucid dreaming as a form of virtual reality produced by the mind itself. Applications include nightmare therapy, rehearsal of motor skills, and creative problem solving. Athletes visualize movements in lucid dreams and show measurable performance gains. Psychotherapists teach patients to confront recurring fears in controlled dream environments, turning passive terror into active mastery. Cultural traditions recognize this potential long before neuroscience. Tibetan dream yoga, practiced for over 1,000 years, trains awareness within dreams to cultivate insight and compassion. Modern imaging shows that advanced practitioners maintain frontal lobe activity even in deep REM, mirroring laboratory lucid dreamers. Science thus confirms what mystics observed empirically: consciousness can remain continuous across states. The connection to sleep paralysis becomes clear here. Both phenomena expose the seams between body and mind. In paralysis, awareness intrudes into the sleeping body. In lucid dreaming, it intrudes into the dream world. Each reveals that consciousness is flexible, capable of existing outside its usual coordinates of space and action. By comparing them, scientists hope to map the architecture of awareness itself. Memory studies reveal intriguing contrasts. Paralysis episodes are remembered with exceptional clarity, perhaps because of adrenaline and fear. Lucid dreams, though equally vivid, fade quickly unless recorded. Keeping a dream journal strengthens recall and increases lucid frequency, suggesting a feedback loop between attention and awareness. Focusing on inner experience during the day correlates with mindfulness during sleep. The deeper question persists: why does the brain produce dreams at all? Evolutionary theories offer several answers. One posits that dreams simulate threats, allowing rehearsal of survival strategies and safety. Another suggests they integrate social information, testing emotional scenarios. Both explain why dream content often centers on pursuit, conflict, or relationships. By imagining dangers and dialogues, the brain refines behavior. Recent computational models treat dreaming as a kind of data optimization. During waking life, prediction errors accumulate, mismatches between expectation and reality. Dreams reshuffle those memories to minimize conflict, updating the brain's internal model. In that sense, dreaming is nightly maintenance of the mind's operating system. From this perspective, sleep paralysis is a brief system glitch. The brain begins the update, but the body exits standby too soon. The result is overlapping programs, one simulating, one perceiving. The fascination of both states lies in how seamlessly the mind can navigate contradictions, accepting impossible realities without question until awakening resolves them. Experiments with pharmacology reinforce the link between chemistry and content. Drugs that suppress REM, such as certain antidepressants, reduce both dreaming and paralysis. Compounds that enhance acetylcholine, like galantamine, increase dream vividness and lucidity. This biochemical control shows that consciousness can be modulated through measurable pathways, grounding even the strangest experiences in physiology. Ethically, researchers tread carefully. The goal is not to engineer perpetual lucidity, but to understand the boundaries of natural consciousness. Each discovery raises philosophical questions. If perception can be created internally, what distinguishes waking reality from a dream stable enough to agree upon? The exploration of sleep thus becomes an exploration of ontology, the nature of being itself. As the study of dreams expands, so does its therapeutic promise. Nightmare disorder, PTSD, and anxiety benefit from lucid dream training and education about RM phenomena. Patients who learn to recognize dream signs report empowerment rather than helplessness. Understanding breeds calm. Calm alters biology. Biology changes experience. A circle as elegant as any equation. And yet, despite decades of research, dreaming retains mystery. Every night, billions of minds generate worlds, stories, and emotions, then erase them upon waking. Only fragments remain: a face, a voice, a sensation of flight. Perhaps that forgetting is functional. To live fully in waking life, the brain must clear the stage each morning. Total recall might blur the lines too much. Still, the glimpse remains powerful. To awaken from a lucid dream or a paralysis episode is to realize how easily reality can be rebuilt from within. The same neural circuits that paint the world around us also paint the worlds inside us. Knowing this can inspire humility and wonder in equal measure. As night yields to early light and brainwaves shift from theta to alpha, most sleepers never remember the silent symphony that has played through their neurons. A few awaken with stories. Fewer still awaken within the stories themselves. They are witnesses to the architecture of consciousness, explorers of the mind's night laboratory. And as their eyes open, another question begins to rise with the sun. If the brain can create a world so convincing while we sleep, how certain can we ever be that the world we wake into is entirely real? Every dream, every flicker of night awareness is shaped by chemistry. Beneath the imagery and the stories lies a continuous flow of molecules moving through blood and brain, shifting moods and perception with exquisite precision. The contrast between terror and serenity during sleep paralysis, or between nightmare and peaceful dream, begins here, in the silent dialogue between hormones, neurotransmitters, and neurons that never truly rest. Cortisol, adrenaline, noradrenaline, dopamine, serotonin, melatonin, these familiar names form the alphabet of our nightly inner weather. Their balance determines whether the sleeping mind drifts smoothly through its cycles or jolts awake in panic. Understanding them reveals that emotions are not intruders in sleep, they are its architects. When stress accumulates through the day, cortisol levels remain high into the night. Elevated cortisol delays sleep onset, shortens deep stages, and lengthens the transitions where REM intrusions can occur. The brain that should slide effortlessly between phases begins to stumble. Sleep paralysis often appears during those stumbles. The person who lies down with unprocessed stress carries it directly into the neural chemistry of dreaming. Adrenaline, the companion of cortisol, surges during both fear and excitement. In ordinary REM, the body is insulated from its effects by paralysis. When awareness returns too soon, that adrenaline is still circulating, amplifying every sensation. The pounding heart and racing breath of paralysis are chemical echoes of survival instinct, not evidence of external threat. Measuring adrenaline levels during recorded episodes confirms this. A spike precedes the moment subjects report a presence. Biology creates emotion. Emotion paints perception. Countering these activating forces are serotonin and melatonin. Serotonin stabilizes mood. Melatonin, secreted by the pineal gland as darkness falls, tells the body it is time to rest. Together, they orchestrate the descent into sleep. Artificial light, caffeine, and irregular schedules all disrupt melatonin's rhythm, delaying its peak and scattering REM cycles. The result is restless sleep where boundaries blur, the ideal breeding ground for vivid dreams and partial awakenings. Inside the brain, The balance between gamma-aminobutyric acid GABA and glutamate determines the level of neural calm. GABA quiets activity, promoting smooth transitions. Glutamate excites, encouraging firing and plasticity. During stable sleep, they alternate like waves on a shore. But when worry or stimulation dominates the day, glutamate remains elevated, and the first hours of night carry residual alertness. It is then that people hover at the edge of wakefulness, easily startled by their own thoughts. Neuroscientists studying this chemistry often remark on how little difference separates fear from curiosity at the molecular level. Both states release similar neurotransmitters. The distinction lies in context and interpretation. The same surge that fuels terror in paralysis fuels fascination in lucid dreaming. The mind decides whether the chemical message signals danger or discovery. Experiments illustrate this duality vividly. In controlled trials, volunteers trained in relaxation techniques experienced the onset of paralysis, but reported minimal fear. Their adrenaline levels rose, yet heart rate variability, a marker of calm control, remained steady. The body prepared for alarm, the mind declined the invitation. That small refusal transformed panic into observation. Such findings underscore the power of top-down modulation, the brain's ability to influence its own chemistry through expectation and attitude. Mindfulness practice, breathing exercises, and even simple cognitive reassurance activate the parasympathetic nervous system, releasing acetylcholine and slowing the heart. These signals feed back to the brainstem, damping the alarm circuits that would otherwise trigger nightmare imagery. Calm, quite literally, changes the brain's chemistry. The interplay between emotion and sleep extends beyond single nights. Chronic stress reshapes the architecture of sleep itself. Prolonged cortisol exposure reduces slow-wave sleep, the phase responsible for physical restoration, while inflating REM density. Dreams grow longer, stranger, and more emotional. In this sense, anxiety writes itself into dream narrative, ensuring that unresolved feelings find expression when words cannot. Conversely, sustained tranquility rewires the same circuits in the opposite direction. Studies of people who meditate daily show increased spindle activity, brief bursts of synchronized brainwaves, in non-REM stages. These spindles correlate with memory integration and emotional resilience. The nervous system learns peace just as it learns fear. Perhaps the most remarkable demonstration of chemical balance occurs at the moment of awakening. Within seconds, the bloodstream shifts composition, melatonin drops, cortisol rises sharply, and the neurotransmitters governing movement surge. The coordination required for such a transition is immense. On most mornings, it succeeds seamlessly. Only rarely does timing misalign to create paralysis. Each successful awakening is a silent biochemical triumph. Outside the laboratory, environmental chemistry also matters. Diet influences neurotransmitter precursors. Tryptophan from proteins becomes serotonin, vitamin B6, and magnesium act as cofactors. Deficiency or imbalance subtly alters sleep quality. Even the air we breathe affects it. Carbon dioxide levels above 1000 ppm, common in closed bedrooms, reduce slow-wave depth, and increase microarousals. Airing a room can literally change dreams. Hormones linked to reproduction, growth, and aging contribute their own variations. Teenagers, whose circadian clocks run later, naturally fall asleep after midnight. Shift schedules that force early rising create chronic deprivation and higher rates of paralysis. During pregnancy, elevated progesterone promotes deeper sleep, but also more vivid dreaming, likely due to increased blood flow to the brain. In aging, melatonin secretion declines, fragmenting sleep and weakening the boundary between night states. Across life, chemistry shapes the landscape of consciousness. Understanding these mechanisms has practical implications, teaching people how to support their own neurochemistry through routine, light exposure, and stress management reduces sleep disorders dramatically. The lesson echoes one from earlier blocks. Knowledge transforms fear. When biology is demystified, control returns. Yet, there remains an art to applying science. Numbers on charts cannot convey the lived texture of calm, the slow rhythm of breath, the temperature of the room, the weight of the blanket. Those sensory details feed back into the very circuits they soothe. The brain does not merely respond to internal chemistry. It listens constantly to the environment for confirmation of safety. This is why gentle light, steady sounds, and predictable rituals before bed are so effective. They tell the nervous system, all is well, you may let go. In clinics where insomnia and paralysis overlap, therapists now integrate multisensory cues. Soft rhythmic audio, subtle scents like lavender, and mild tactile feedback from weighted blankets combine to anchor the body in the present moment. EEG recordings show increased theta-alpha coherence, a neural signature of relaxation, when such cues are used. The physiology of peace can be engineered as precisely as the physiology of fear. The boundary between emotion and physiology blurs further when considering memory. Each time fear is overcome, the amygdala stores that success. Future episodes trigger milder responses. This process, called extinction learning, gradually rewrites the brain's chemical habits. The person who once woke nightly in terror may, months later, drift through the same paralysis with curiosity, their body producing less adrenaline, more endorphins. Neuroplasticity is the quiet ally of recovery. Endorphins themselves, often overlooked in sleep research, play a subtle role. Released during relaxation and warmth, they create a gentle euphoria that can carry into dreams. Participants in sleep lab studies who fell asleep smiling after laughter or gratitude exercises showed higher endorphin markers and reported more positive dreams. The chemistry of kindness extends even into unconsciousness. At the molecular level, all these processes reduce to electrical signals crossing synapses. Ions moving, receptors opening, tiny changes in voltage, but scale them up to the human experience, and they become emotion, story, and meaning. Sleep paralysis becomes less a haunting and more a conversation between molecules and mind. Still, the mystery remains compelling. Why does such a delicate system exist at all? Why not a simpler design without dreams or paralysis? Evolutionary biology suggests efficiency. REM provides mental rehearsal. Paralysis ensures safety, and emotional modulation fine-tunes learning. The very fragility of the system allows its flexibility. A brain capable of fear is also capable of imagination. Each night's chemistry writes a new equation on that theme. Some nights the formula yields chaos, others, serenity. Yet beneath the variability lies order, a self-regulating rhythm that has sustained our species since the first mammals slept in hidden dens. Fear and calm, action and rest, are not opposites but partners in equilibrium. And as you breathe quietly now, aware of how much invisible coordination sustains even this moment, consider that the same chemistry maintaining your heartbeat also shapes the landscapes of your dreams. Every pulse of blood carries the potential for nightmare or peace, for paralysis or flight. The difference lies only in timing, interpretation, and a few molecules more or less of a single substance. Somewhere tonight, in a research lab or a quiet bedroom, another mind will cross that boundary. Fear dissolving into curiosity, chemistry into consciousness. And the story will continue, molecule by molecule, thought by thought. Every second you live is recorded somewhere inside your brain, but not all of it survives until morning. Sleep is the editor that decides what stays and what fades. Beneath the calm surface of rest, neurons replay, reorganize, and erase. An invisible maintenance shift that determines who you become the next day. Without it, learning stalls, emotions blur, and perception itself begins to distort. Modern imaging has revealed that memory is never a fixed archive. It is a living network that changes each time it is accessed. During wakefulness, the hippocampus, the brain's temporary storage, collects experiences in high-resolution bursts. At night, those traces are transferred to the cortex, compressed and integrated with older knowledge. Slow-wave sleep acts as the courier. REM refines the delivery. Together, they sculpt memory into long-term form. Electroencephalograms show that during deep, non-REM stages, neurons fire in slow synchronized waves. Within those waves ride faster ripples from the hippocampus, like messages carried on a radio signal. Each ripple corresponds to fragments of the day's experiences replaying thousands of times faster than they occurred. In animal studies, researchers can literally predict where a rat dreamed of running by reading those ripples. The same mechanism operates in humans. Replay equals consolidation. If this transfer is disrupted by insomnia, stress, or irregular schedules, memories remain unstable. Experiments in sleep-deprived volunteers show up to 40% reduction in recall after only one night. Emotional regulation suffers even more. The amygdala, deprived of its nightly calibration, becomes hyperreactive. People report irritability, anxiety, and difficulty distinguishing real threats from minor discomforts. In effect, lack of sleep makes the world look more dangerous than it is. The brain also uses sleep to prune. Synapses formed during the day exceed what the system can maintain. At night, weaker connections shrink while stronger ones stabilize. This synaptic homeostasis preserves efficiency and energy balance. It explains why a good night's sleep often clarifies thought. The neural noise has been filtered out. Each morning is not only a continuation but a recreation of the mind. Time perception changes as this housekeeping unfolds. Inside the sleeping brain, subjective duration decouples from real time. Dreams that seem to last hours may occupy seconds of REM. Deep sleep ripples replay minutes of experience in milliseconds. When you wake, consciousness stitches these fragments into narrative order, unaware of the compression. Sleep scientists call this temporal rescaling. It demonstrates that our sense of time is a construct, recalibrated nightly. Another nightly process, glymphatic clearance, cleans the brain physically. Cerebrospinal fluid pulses through spaces between neurons, flushing metabolic waste such as beta amyloid. This fluid movement increases by up to 60% during sleep. Without it, toxins accumulate and cognitive function declines. Sleep paralysis, though unrelated to this plumbing directly, occasionally overlaps with its timing. Brief awakenings during intense glymphatic flow can produce sensations of pressure or movement within the head that the mind interprets as external force. What feels supernatural is sometimes hydraulic. Emotional memory receives special attention during REM. The same limbic circuits active in waking fear, the amygdala and anterior cingulate, reactivate, but cortisol and noradrenaline remain low. The brain replays stressful scenes in a chemically safe environment, removing the sharp edge of emotion. This mechanism, sometimes called overnight therapy, explains why painful events often feel slightly less raw after sleep. Dreams may dramatize fear, but biology uses them to neutralize it. Linking these findings to sleep paralysis closes a circle. Episodes often occur when emotional memories are being processed, but the sleeper wakes before completion. The half-finished replay projects into awareness, mixing with paralysis sensations to create vivid imagery. Understanding this sequence transforms horror into observation. The shadow at the end of the bed may be nothing more than the residue of a memory being edited. Memory research also clarifies why certain dream motifs repeat. Recurring places and faces are not signs of prophecy, but of incomplete integration. The brain revisits unresolved patterns until they fit. Therapy that encourages expression of buried emotion often reduces recurring nightmares, proving that psychological resolution alters neural replay. During aging, the efficiency of this nightly editing declines. Slow wave amplitude decreases, and hippocampal ripples lose synchronization with cortical waves. Older adults therefore rely more on repetition in learning. Their brains simply consolidate less per night. Interventions like exercise, exposure to morning light, and cognitive stimulation can restore part of the rhythm, showing that the system remains plastic throughout life. Perhaps the most intriguing discoveries come from studies combining fMRI and EEG to visualize dreams forming in real time. When volunteers were awakened during specific patterns, they could describe imagery that matched activated brain regions, faces when fusiform areas lit, movement when motor cortex flared, speech when language zones pulsed. The implication is extraordinary. Every night, the brain generates internal movies with the same machinery it uses to perceive the world by day. From a philosophical angle, this suggests that perception itself is memory in progress. Waking consciousness relies on continual prediction, informed by stored experience. Dreams reverse the process, letting memory predict without constraint. In both, reality is a negotiation between past and present signals. The nightly maintenance extends to identity. Studies show that self-referential brain regions, the medial prefrontal cortex and posterior cingulate, activate during dreams, featuring the dreamer's own perspective. The brain rehearses the sense of I, integrating new experiences into the story of self. After major life changes, dream content shifts accordingly, helping the mind adjust to new realities. Sleep, therefore, acts as both archive and author of personal continuity. When sleep fragmentation prevents this rewriting, identity coherence weakens. People describe feeling detached, forgetful, or unreal, a condition known as derealization. Restoring stable sleep often resolves it, confirming that a consistent self depends on consistent restoration. The scale of coordination required for all this is staggering. Billions of neurons communicate in patterns so precise that even tiny timing errors can alter mood or cognition. Yet the system runs automatically, night after night, guided by circadian genes that anticipate sunrise and sunset. The same molecular clocks tick in every cell, from liver to skin, synchronized by light. Sleep is not absence, but alignment. As you imagine these processes unfolding, the waves of electrical replay, the silent rivers of cerebrospinal fluid, the microscopic pruning of synapses, it becomes clear that rest is not idleness. It is work of the highest order, maintaining the machinery of consciousness itself. We awake each day rebuilt from the inside, and somewhere in that rebuilding lies another puzzle. If memories are rewritten nightly, then the self we remember from yesterday is already an edited version. The continuity we feel may be as carefully constructed as any dream, which raises the quiet question that follows you into morning. When you open your eyes, who exactly is it that wakes? Every human being lives inside a private model of the world. Light strikes the retina, vibrations touch the ear, molecules stimulate the nose. Yet none of these sensations exist as we experience them until the brain transforms them into color, sound, and meaning. The waking world is a controlled hallucination that happens to agree with the hallucinations of others. Sleep exposes this fact by loosening the rules. In waking life, sensory input dominates. In dreams, internal prediction takes over. Both rely on the same neural scaffolding, networks that continuously guess what is out there. Neuroscientists call this predictive coding. The brain compares incoming data with expectations. When the match is good, perception feels stable. When it fails, confusion, illusion, or paralysis arise. The difference between seeing a shadow and seeing a figure during sleep paralysis is not in the eyes, but in the prediction the brain chooses. Functional imaging confirms this hierarchy. Visual cortex receives raw data, but interpretation comes from higher levels, parietal and frontal regions that supply context. During REM, these higher areas remain active, generating expectations without external input. The result: internally consistent virtual reality. When partial awakening occurs, both data streams, dream and environment, compete, producing hybrid scenes, too coherent to dismiss yet too strange to trust. Perception scientists test this principle while subjects are awake using illusions, shifting checkerboards, ambiguous faces, the rubber hand trick. The same brain mechanisms that merge sight and touch in those experiments operate during dreaming. Sleep paralysis is simply an illusion we enter instead of observe. Every sense participates. Touch, for example, depends on the body's schema, the brain's internal map of limb position. When motor feedback is cut off, as in paralysis, this map becomes unstable. Sensations of floating or pressure appear as the mind recalibrates. Hearing behaves. Similarly, deprived of real sound, auditory cortex amplifies internal noise until it forms whispers or footsteps. Even temperature perception can invert. Reports of icy presence or burning heat correspond to mismatched activation in the insula, where bodily states are modeled. Understanding these constructions helps clarify everyday reality. Waking perception feels solid only because feedback from the body constantly corrects prediction errors. Remove that feedback, and imagination rushes in. The same machinery that lets an artist visualize a painting or an engineer foresee a design fills the darkness of paralysis with figures and voices. Creativity and hallucination share roots. Philosophers have long suspected this. Plato's cave, Descartes' demon, Kant's categories, all anticipated that experience is filtered. Neuroscience now maps those filters precisely. Each moment, the brain integrates millions of signals, yet shows consciousness only a summary. Dreams prove how convincing that summary can be, even when detached from reality. In both states, belief is the final ingredient that makes perception feel real. Belief itself has measurable circuitry, the anterior cingulate and prefrontal cortex, evaluate uncertainty, while dopamine systems assign confidence to predictions. During REM, these evaluators relax. The improbable becomes plausible. The mind accepts flying or meeting the dead without hesitation. In paralysis, the same suspension of disbelief merges with sensory confusion to create absolute conviction that someone else is present. The power of belief is biological. Researchers exploring this with magnetoencephalography find that oscillations in the beta band, associated with prediction maintenance, drop sharply when people enter altered states. Low beta means the brain updates its model freely, allowing imagination to overwrite input. When awareness returns before beta stabilizes, hallucination lingers for seconds, explaining why figures dissolve gradually after paralysis ends. Culture shapes which predictions fill the void. A believer in spirits expects spirits. A skeptic expects intruders. The content changes, the mechanism remains. Studies comparing different countries reveal identical neural signatures beneath diverse narratives. The human brain, regardless of language or faith, resolves uncertainty the same way, by creating story. Daylight offers its own illusions, motion after effects, phantom vibrations from silent phones, voices heard in white noise. Each demonstrates the predictive system overshooting its mark. Sleep simply magnifies this everyday tendency. The border between imagination and perception is thinner than comfort suggests. Understanding this architecture has practical use. Therapies for hallucination, PTSD, and anxiety increasingly focus on recalibrating prediction. Exposure therapy works by providing safe feedback until the brain revises its expectation of danger. Mindfulness works by reducing the weight of prediction altogether, letting sensory data arrive without judgment. In that sense, meditation and scientific training aim for the same goal: clearer models of reality. Consciousness researchers extend this reasoning further. If perception is prediction confirmed, then awareness might be the process of prediction itself, a continuous monitoring of model accuracy. Under anesthesia, predictive loops break. Under psychedelics, they loosen. In deep meditation, they quiet. Sleep paralysis represents another variation, intact consciousness observing an unstable model. The unity of experience across such states suggests a single underlying principle. The brain is not a camera, but a storyteller. It constructs the self as protagonist and the world as setting, updating both through sensory evidence. When that evidence falters, as in the night, the story continues on internal fuel. To realize this is not to diminish reality, but to appreciate its craftsmanship. Time, again, behaves strangely inside this model, because prediction relies on sequence. When sensory input pauses, the brain may replay or stretch events to maintain coherence. Dream minutes become waking seconds. Paralysis seconds feel like minutes. The subjective inflation of time mirrors the inflation of meaning. The mind compensates for missing data by deepening emotion. Even the sense of location, the feeling of being somewhere, is predicted. In out-of-body experiences, activity shifts from the posterior parietal cortex to the temporoparietal junction, where multisensory information converges. When input conflicts, the brain projects the self outside its usual coordinates. Sleep paralysis often involves this same dislocation, revealing that I is not fixed but computed. Philosophers of consciousness debate whether this computation creates or merely represents awareness. Empirical data lean toward creation. When predictive hierarchies collapse, awareness fragments. Yet subjective reports during deep meditation or lucid dreams suggest that a core sense of presence persists even without ordinary perception. Perhaps consciousness is the capacity to model any world, not necessarily the physical one. Practical implications follow. Recognizing perception as construction allows compassion. When another person experiences fear, pain, or joy, their brain's model differs from yours, but feels equally real to them. This understanding dissolves judgment. In the context of sleep phenomena, it reminds sufferers that terror is not weakness. It is the mind doing its best to interpret limited data. Technological advances may soon let us visualize these models directly. Decoding algorithms already reconstruct dream imagery from fMRI patterns with surprising accuracy. The same methods could map hallucinations during paralysis, turning private visions into data. Such tools raise ethical questions. How much of inner experience should be observable? Science approaches mysteries once reserved for philosophy, and humility becomes essential. At the personal level, the lesson remains grounding. Each time you wake from a vivid dream or a night of paralysis, you return to a consensus reality negotiated by billions of brains. It is stable enough for shared life, yet flexible enough for imagination. The fragility that causes nightmares is the same flexibility that enables creativity, empathy, and hope. As night deepens again, billions of predictive engines will power down and rebuild. Some will drift into gentle dreams, some into lucid landscapes, a few into paralysis. All will be practicing the same ancient skill, creating a world from within. The darkness outside the eyelids is only half the night. The rest unfolds behind the eyes. And when morning arrives and light floods the retinas, the brain will once more align its model with the external world, confident that what it sees is real, though it knows, somewhere deep within, that reality is always partly imagined. Every living thing on Earth, from a blade of grass to a human being, keeps time. Long before mechanical clocks or calendars, life learned to predict the cycle of light and dark. Inside every cell, molecular gears turn with astonishing precision, telling tissues when to rest, when to repair, and when to wake. This hidden machinery is the circadian system, a 24-hour rhythm written into our DNA. At the center of this system sits the suprachiasmatic nucleus SCN, two clusters of about 20,000 neurons nestled deep within the hypothalamus. Each morning, when light enters the eyes, specialized photoreceptors send signals directly to the SCN, resetting its phase. From there, chemical messengers ripple outward through the body, aligning heart rate, hormone release, digestion, and temperature to the new day. The SCN is only the conductor. Every organ has its own clock. Together they form a biological orchestra that must stay in tune. When the system runs smoothly, alertness peaks in late morning, body temperature in mid-afternoon, and sleep pressure rises gently after dusk. But in modern life, artificial light, shift work, and irregular routines constantly detune the ensemble. Blue light from screens after sunset tricks the brain into delaying melatonin secretion, pushing sleep later. Jet lag, night shifts, or even weekend sleep-ins scramble the rhythm further. The mismatch between internal and external time is called social jet lag, and it affects mood, metabolism, and immune function. Experiments with volunteers kept in underground bunkers without clocks or windows prove that the internal day is slightly longer than 24 hours, about 24.2. Without sunlight to reset it, the rhythm drifts, causing gradual delay of sleep and wake times. Light is the anchor that prevents this drift. Its absence in winter contributes to seasonal affective disorder, while proper exposure in the morning can lift mood and improve concentration. A simple walk at sunrise is one of the most powerful synchronizers available. Temperature is another cue. Body heat follows a daily wave, highest in late afternoon, lowest a few hours before dawn. Falling temperature signals the brain to release melatonin and deepen sleep. A cool bedroom, around 18 degrees Celsius, helps this process, while overheating suppresses RM. The comfort we associate with a slightly chilled room is not psychological, it's thermodynamic alignment with the circadian curve. Hormones dance to this clockwork too. Cortisol surges just before waking, providing the energy to rise. Insulin sensitivity peaks at midday, making daytime meals easier to metabolize. Growth hormone pulses during early night, repairing tissues, disturb the schedule, and these peaks flatten. Chronic night work has been linked to metabolic disorders precisely because hormones lose rhythm, not because workers eat differently. Even gut bacteria follow the pattern. Microbes in the intestine change composition and activity across the day, influenced by our feeding times. Irregular meals confuse them, leading to inflammation and discomfort. Synchronizing meals with daylight helps restore microbial balance, an ancient partnership between human and microbe tuned to the sun. The connection between circadian rhythm and mental health is equally strong. Patients with depression or bipolar disorder often show disrupted sleep-wake cycles. Correcting light exposure and timing can stabilize mood. Cognitive performance, reaction time, and emotional regulation all oscillate predictably through the day. Understanding one's personal rhythm, one's chronotype, allows scheduling demanding tasks at natural peaks rather than against them. Sleep paralysis and vivid dreams tend to cluster near transitions when circadian signals conflict, early morning or after irregular nights. Jet lag, new parenthood, or exam stress create fertile ground for overlap between REM and waking. The lesson repeats. Stability is protection. The body's clock is not fragile, but it resists sudden change. Laboratory chronobiologists study these cycles with remarkable precision. Volunteers live for weeks in windowless rooms under controlled light, while their body temperature, hormones, and alertness are measured hourly. From these data, researchers construct phase maps showing how every physiological variable oscillates. The beauty of these graphs is their unity. Separate systems, heart, liver, skin, all trace the same cosmic rhythm, lagging only by minutes. We are, literally, organisms of light. Artificial light technology now attempts to work with rather than against this design. Human-centric lighting in hospitals and offices gradually shifts color temperature through the day, supporting natural alertness and evening calm. Astronauts on the International Space Station use programmable LEDs to simulate Earth's day-night cycle and reduce insomnia. As science understands circadian biology, architecture and medicine converge. For individuals, simple habits harness the same principle. Exposure to bright light soon after waking anchors the rhythm. Dimming lights 2 hours before bed invites melatonin to rise. Consistency, sleeping and waking at similar times, strengthens the signal so powerfully that even occasional disruptions recover quickly. The rhythm rewards respect with energy and emotional stability. Shift workers, whose schedules oppose daylight, face special challenges. Strategic light exposure, controlled naps, and careful caffeine timing can reduce damage, but no intervention fully replaces natural alignment. Health guidelines now classify chronic night work as a probable carcinogen, not because of toxins, but because cellular repair genes depend on time cues. At night, those genes expect darkness. The molecular mechanism behind all this timing resides in feedback loops of genes such as clock, BMAL1, purr, and cry. These genes turn on and off in roughly 24-hour cycles, producing proteins that inhibit their own expression. The oscillation runs autonomously in cultured cells, even without a brain. It is one of biology's most elegant designs. Time is chemistry, ticking within every nucleus. Disruption of these loops can cause striking effects. Mice with defective clock genes lose rhythm entirely, sleeping and waking randomly. Humans with certain variants experience delayed sleep phase syndrome, finding it almost impossible to fall asleep before dawn. Understanding these genetic underpinnings transforms the problem from moral, lazy, to medical, and guides treatment through light therapy and scheduling rather than willpower. Circadian rhythm also governs learning. Memory formation peaks when cortisol and body temperature are moderate, typically midday. Studying at that time yields better retention than late-night cramming, yet cultural habits often reverse it. Education could benefit simply by aligning class times with biology. Dream content subtly reflects circadian phase. Early night dreams, when slow-wave sleep dominates, tend to involve realistic events and problem-solving. Late morning REM dreams, under high cortisol, become emotional and surreal. The clock paints the tone of the dream world. Perhaps the most poetic aspect of circadian rhythm is its universality. Flies, plants, fungi, humans, all obey the same basic equations of feedback and delay. Evolution has preserved it for over 3 billion years because it links life to the planet's rotation. Every heartbeat, every hormone pulse, every thought is, in some sense, a dialogue with the sun. Recognizing this connection reframes rest not as withdrawal, but as participation in a cosmic pattern. When you sleep, you are not stepping outside time, you are aligning with it. The light that wakes you in the morning is the same light that synchronized ancestors and ecosystems long before history. To live against that light is to live out of tune. To live with it is to move in rhythm with the world. And so the study of sleep, dreams, and paralysis ultimately returns to this. Timing. Consciousness itself is rhythmic. Waves within waves, oscillations of neurons echoing the turning earth. When the pattern holds, we call it health. When it slips, we call it disorder. But beneath both lies the same pulse, ancient and continuous, counting out the seconds of life. Somewhere right now, as darkness spreads across one hemisphere and dawn touches another, millions of clocks inside millions of bodies shift phase together. The planet breathes in rhythm with its creatures, and every sleeper, knowingly or not, keeps time with the stars. For most of human history, night meant darkness, silence, and stars. Only in the last 2 centuries has the world learned to banish the dark. With that victory came an unforeseen cost: the erosion of natural sleep. The modern night glows with street lamps, screens, and endless information. The same technologies that extend productivity shorten rest. Biology evolved for rhythms of sunrise and sunset. Civilization now runs 24 hours a day. Electric light began the change. In 1879, when Edison's bulb turned night into day, people could read, work, and socialize after dusk. Average sleep time soon fell from 9 hours to about 7. Gaslight had already shifted habits, but electricity made brightness universal. Cities no longer slept. Factories and offices rotated shifts. Entertainment filled every hour. The human circadian system, tuned for gradual twilight, suddenly faced permanent noon. Light at night confuses the brain because vision and timekeeping share a pathway. Photoreceptors in the retina, called intrinsically photosensitive ganglion cells, contain melanopsin, a pigment most sensitive to blue wavelengths. When stimulated, they suppress melatonin and signal wakefulness. LED screens, optimized for vivid color, emit exactly this blue spectrum. Checking a phone in bed is like shining morning into the eyes. Even brief exposure delays sleep by increasing alertness and shifting the body clock later. In laboratory studies, volunteers reading from tablets before bed took longer to fall asleep, produced less melatonin, and felt sleepier the next morning. Their error proportion fell by up to 20%. The difference seems small, but accumulates. Over weeks, chronic light exposure after dark fragments, sleep architecture, increases cortisol and alters metabolism. The result is fatigue disguised as productivity. Noise joins light as a silent saboteur. Urban soundscapes rarely fall below 30 decibels. Distant traffic or appliances maintain constant low-level stimulation. Even when sleepers do not wake fully, microarousals punctuate the night, preventing deep rest. Heart rate and blood pressure rise imperceptibly, yet the cardiovascular system feels the strain. The WHO estimates that chronic nighttime noise costs millions of healthy life years across Europe alone. Unlike ancient threats that triggered momentary alarm, modern noise is continuous. The brain never receives the all clear. This constant vigilance explains why city dwellers often dream of pursuit or intrusion. Their nervous systems rehearse danger that never ends. Studies using noise-insulated bedrooms show immediate improvement in sleep depth and mood, proving that quiet is medicine. Temperature adds another challenge. Central heating and sealed buildings create stable climates but prevent the small nightly cooling that triggers melatonin release. Air-conditioned nights can stay too cold early and too warm toward dawn, disturbing the natural curve. Ideal sleep follows a gentle decline of 1 to 2 degrees Celsius. After sunset, constant temperature confuses the signal. Opening a window or lowering the thermostat restores a cue evolution expects. Caffeine and artificial light reinforce each other. Both suppress adenosine, the molecule that builds sleep pressure. The modern evening often includes coffee, energy drinks, or soft beverages hours after dinner. Caffeine's half-life is about 6 hours. A cup at 6 p.m. leaves a quarter of its stimulant active at midnight. Combine that with bright screens and mental engagement, and sleep pressure never reaches threshold. Fatigue accumulates invisibly behind stimulation. Technology extends influence beyond physiology into psychology. The internet removes closure from the day. Social media and streaming provide endless novelty, keeping dopamine circuits active long after the body wishes to rest. The brain, designed to seek patterns and reward, becomes trapped in an infinite loop of scrolling. Each small piece of information promises completion, but delivers more anticipation. This intermittent reinforcement pattern mirrors the structure of addiction. Cognitive scientists call this attention capture. Every notification acts as a microstimulus of curiosity, releasing dopamine that momentarily raises alertness. At night, this pattern competes directly with melatonin's calming effect. The result is a mind chemically primed for vigilance at precisely the hour it should surrender. Surveys show that over 60% of adults check their phones within 5 minutes of waking and before sleep, creating a feedback loop that erodes boundaries between rest and activity. Sleep specialists now describe a condition informally known as revenge bedtime procrastination. After long days of external demands, individuals delay sleep to reclaim personal time, scrolling or watching videos despite exhaustion. The behavior feels like freedom, but steals restoration. Psychologically, it reflects the tension between autonomy and biological need. Recognizing it is the first step toward balance. Part 1 ends here, showing how artificial light, noise, temperature control, caffeine, and digital attention have transformed the modern night into perpetual twilight. Next, Part 2 of 4 explores how cities and technology reshape circadian biology and the measurable consequences for physical and mental health. The modern city never truly sleeps. Its light spills upward into the sky and downward through every window, scattering photons that erase the boundary between day and night. From orbit, the continents glow like constellations reversed, human stars against the dark. For astronomers, this light pollution hides the Milky Way. For biologists, it hides the ancestral cues that once governed physiology. Studies comparing rural and urban populations reveal striking differences. In villages without artificial light, melatonin levels rise within minutes of sunset, peaking near midnight. In cities, the same curve flattens and shifts 2 to 3 hours later. People fall asleep later, wake earlier for work, and accumulate chronic sleep debt. The pattern mirrors jet lag but repeats daily. Chronic misalignment increases appetite hormones like ghrelin, reduces leptin, and disrupts glucose control. A phenomenon born of light becomes a driver of modern metabolic disease. Mental health follows the same curve. Insomnia correlates strongly with anxiety and depression, but the relationship is bidirectional. Sleeplessness amplifies negative mood, and negative mood resists sleep. Bright light after dark extends alertness and suppresses serotonin conversion into melatonin, creating chemical contradiction, wakefulness bathed in fatigue. Over weeks, this imbalance dulls emotional regulation. The amygdala reacts more intensely to stress, the prefrontal cortex less able to moderate it. The modern night quietly reshapes temperament. Technological overexposure adds a cognitive layer. Blue-lit workspaces and late-night emails keep cortical networks engaged in problem-solving long after tasks end. EEG readings show sustained high-frequency beta activity in people who use digital devices before bed, while those who unwind with analog activities, reading paper, gentle conversation, shift smoothly into slower alpha waves conducive to sleep. The difference appears minor, yet defines whether consciousness drifts easily or clings to thought. Even color influences rest. Experiments using dynamic lighting demonstrate that warm, amber tones promote melatonin release and parasympathetic activation, whereas cold white light prolongs vigilance. Interior designers now collaborate with chronobiologists to create circadian lighting, systems that mimic sunset hues indoors. The aim is not nostalgia, but neurochemistry, returning modern environments to a spectrum the brain recognizes as evening. Urban architecture amplifies another disruptor: noise complexity. Sound waves ricochet between buildings, blending into constant low-frequency hums that ears cease to notice but brains cannot ignore. EEG microarousals appear even when sleepers report silence. These fragment deep sleep, particularly slow-wave stages vital for immune restoration. Residents near airports or major roads display higher cortisol levels each morning, despite closed windows. Earplugs, double glazing, and acoustic insulation mitigate, but seldom eliminate the effect. The true remedy would be quieter cities. Sociologists describe a cultural dimension, the valorization of busyness. In many societies, short sleep has become a badge of productivity, a marker of ambition. Surveys of executives and students alike reveal pride in minimal rest. Yet performance studies contradict the myth. Cognitive impairment after 17 hours awake equals that from a blood alcohol concentration of 0.05%. Sleepless efficiency is self-deception, measured in milliseconds of slower reaction and errors unnoticed. Technology companies now attempt to reverse the damage they helped create. Night mode filters reduce blue light, wearable devices track circadian trends, and apps encourage digital sunsets. Data from millions of users confirm familiar truths. Consistent schedules in darkness remain superior to any algorithm. Still, awareness grows. Design is learning to serve biology again. Cities experiment too. Some switch streetlights to warmer spectrums, dim them after midnight, or install motion sensing systems that preserve safety while restoring darkness. Hospitals implement lighting cycles for shift workers and patients, reducing delirium and fatigue. Airlines adjust cabin illumination and meal timing to align passengers with destination time zones. Everywhere, the concept of circadian design spreads quietly, reintroducing rhythm into 24-hour culture. Yet challenges remain psychological. The human craving for connection and novelty, once satisfied by village gatherings under firelight, now extends through digital networks that never close. Social media algorithms reward immediacy, creating pressure to respond across time zones. Sleep becomes negotiable. Presence online replaces presence in bed. Sociologists call it temporal colonization, technology occupying the hours once reserved for rest. Within the individual, this occupation manifests as subtle anxiety. The brain's default mode network, responsible for reflection and memory integration, requires quiet intervals. When notifications punctuate every pause, introspection shortens, emotional processing stalls, and dreams inherit unfinished thoughts. The fragmented attention of day becomes the fragmented imagery of night. Neuroscientists studying digital fatigue note overlapping symptoms with chronic sleep deprivation, irritability, reduced empathy, memory lapses. Both involve diminished prefrontal control and elevated limbic activity. In effect, the always connected brain lives in perpetual mild jet lag. The term infosomnia has entered research literature to describe this hybrid exhaustion. Despite the data, adaptation is possible. Evening routines that deliberately counteract stimulation, dimming lights, silencing devices, performing repetitive calming actions, signal the nervous system to shift modes. The transition need not be long. Even 15 minutes of consistent ritual rewires expectation. Over time, the body associates those cues with rest, releasing melatonin more predictably. Ancient practices like evening prayer or storytelling served precisely this purpose, communal cues for the brain to disengage. Still, one question haunts chronobiologists. Can humans truly coexist with constant illumination without consequence? Some argue evolution will adjust. Others warn that the mismatch between genetics forged in darkness and lifestyles drenched in light cannot close in mere centuries. Evidence leans toward the latter. Genes change slowly. Habits change overnight. The result is an era of luminous fatigue, and yet, beneath the glare, the ancient rhythm endures. Every human cell continues to count the hours faithfully, waiting for darkness that never fully comes. Perhaps the modern task is not to defeat the night, but to restore it. Not through nostalgia, but through understanding. Sleep loss does not announce itself dramatically. It accumulates quietly, an invisible debt measured not in hours missed, but in systems slowly unbalanced. Modern life treats sleep as expendable, yet biology treats it as fundamental as breathing. Each cell in the body expects darkness, rest, and rhythmic chemistry. When those signals falter, consequences ripple outward, from genes to mood, from digestion to empathy. The first system to show strain is metabolism. In controlled studies, healthy volunteers limited to 4 or 5 hours of sleep for a week develop insulin resistance comparable to that seen in prediabetes. Their fasting glucose rises, leptin drops, ghrelin increases, and appetite surges, especially for carbohydrates. The body interprets fatigue as famine, demanding quick energy. Nightly recovery corrects this within days, demonstrating that the effect is reversible but relentless. Cortisol, the hormone of wakefulness and stress, becomes another casualty. Normally highest in the morning and lowest at midnight, its rhythm flattens under chronic sleep loss. Constant elevation keeps the sympathetic nervous system active, raising blood pressure and storing fat around the abdomen. Over months, this metabolic shift links sleep restriction to obesity and cardiovascular disease. Epidemiological data spanning millions show a clear gradient. The shorter the habitual sleep, the higher the risk of hypertension, stroke, and diabetes. Inflammation joins the cascade. Even partial deprivation increases circulating cytokines, chemical messengers that coordinate immune defense. When produced chronically, they erode tissues rather than protect them. C-reactive protein, an inflammation marker and predictor of heart disease, rises measurably after a single night of poor sleep. The immune system, deprived of its nightly calibration, confuses friend with foe. It becomes edgy, hyper-alert, and prone to misfire. Immunity itself weakens. Volunteers who received a standard cold virus after sleeping less than 6 hours were 4 times more likely to develop symptoms than those who slept more than 7. Vaccine responses follow the same pattern, reduced antibody production when sleep is curtailed. The mechanism is straightforward. Slow-wave sleep fosters cytokine balance and B-cell activation. Without it, the body's defenses forget the choreography. Reproductive hormones decline as well. In men, testosterone drops by up to 15% after a week of curtailed sleep, a change usually seen after a decade of aging. Women experience disruptions in luteinizing hormone and menstrual regularity. Fertility clinics increasingly consider sleep hygiene part of treatment, not lifestyle advice. The endocrine system listens closely to the clock. The brain, though, bears the most visible cost. Functional MRI studies show reduced activity in the prefrontal cortex after sleep restriction, the very area responsible for planning, impulse control, and decision-making. Simultaneously, the amygdala, the seat of emotion, becomes hyper-responsive. The result is mood volatility, anger, sadness, and anxiety magnified, judgment dulled. In a sense, the tired brain reverts to adolescence, reactive, creative perhaps, but unstable. Memory suffers too. The hippocampus requires both slow-wave and REM sleep to consolidate learning. Deprivation short-circuits this process. Students pulling all-nighters recall up to 40% less material than peers who sleep normally. Worse, the brain cannot recognize the deficit. Subjects rate their performance as adequate even when objective tests show decline. Fatigue impairs insight into fatigue, a dangerous blind spot. Attention networks fragment. Microsleeps, brief lapses of consciousness lasting seconds, invade wakefulness. On highways or in factories, those seconds can be fatal. In 2017, a meta-analysis of industrial accidents revealed that night shift workers faced a 30% higher risk of serious error, largely due to circadian misalignment and insufficient rest. Technology may extend capacity, but biology retains veto power. Creativity and empathy fade more subtly. When prefrontal control weakens, social interpretation falters. Experiments using facial emotion recognition show that sleep-deprived participants misread neutral expressions as hostile. The same misperception fuels conflict in workplaces and families. A single bad night can make the world appear more threatening and less kind. Conversely, adequate sleep restores nuance. Compassion itself depends on circadian stability. Chronic deprivation alters perception of pain. The insula and somatosensory cortex amplify signals from the body when deprived of REM. Subjects report heightened discomfort from identical stimuli. Hospitals that protect patients' sleep. Not merely rest, but darkness, reduced interruptions, and timing medication around cycles. See faster recovery and lower analgesic use. Healing, it seems, is rhythm made visible. Neurochemically, dopamine plays an ambiguous role. Fatigue lowers baseline dopamine but increases receptor sensitivity, producing brief bursts of motivation followed by crashes. This seesaw fuels reliance on stimulants, coffee, energy drinks, or digital excitement to maintain alertness. The temporary lift masks underlying exhaustion, creating dependency. Over time, the brain associates productivity with stimulation rather than recovery, reinforcing insomnia. At the genetic level, sleep loss rewrites expression patterns. After 1 week of 5-hour nights, researchers found activity changes in over 700 genes. Half increased expression of stress and inflammation pathways, half suppressed immune and repair functions. The effect reversed after recovery sleep, showing resilience. Yet the message is clear. Sleep is not rest from biology. It is participation in it. Even cellular aging accelerates. Telomeres, the protective caps at chromosome ends, shorten faster in people who habitually sleep fewer than 6 hours. Though modest, the effect compounds across decades. The body keeps a quiet record of every lost night in its DNA. Cardiologists now view sleep as the third pillar of health, beside diet and exercise. The triad is inseparable. Neglect one, and the others fail. Physical training without recovery impairs muscle repair. Nutrition without rhythm confuses metabolism. Medicine increasingly prescribes darkness and silence alongside diet and movement. The societal cost of sleeplessness rivals any epidemic. Economists estimate hundreds of billions lost annually to fatigue-related errors, absenteeism, and medical expenses. Yet the deeper cost may be cultural. A collective dulling of attention and patience. A chronically tired society reacts faster and reflects less. Speed replaces depth. News cycles shorten, empathy narrows, creativity fragments. The modern night, once a space for reflection, becomes another arena of productivity. Still, within the same environment, recovery remains possible. Studies show that consistent 8-hour nights for 2 weeks reverse most metabolic and cognitive deficits. The body forgives quickly when given the chance. Sleep is not luxury but repair, and the repair starts the moment darkness returns. Recovery from chronic sleep loss follows biological logic. First, the body restores energy balance, then the mind repairs cognition, and finally mood stabilizes. The sequence unfolds over several nights. During the first 8 hours of true rest, slow-wave sleep dominates. The next few cycles reclaim REM. People often report unusually vivid dreams after periods of deprivation. These rebound dreams are not psychological excess, but neurological compensation. REM catching up on unfinished processing. Inside the brain, glial cells, the silent partners of neurons, expand their cleaning work. The glymphatic system flushes metabolites that build up during wakefulness, especially beta amyloid and tau proteins associated with neurodegeneration. Regular clearance keeps synapses flexible. When sleep remains restricted, waste accumulates, setting the stage for cognitive decline later in life. Longitudinal studies show that individuals sleeping fewer than 6 hours for decades face a sharply increased risk of dementia. Sleep may be the most accessible form of neuroprotection. The relationship between sleep and mood is equally circular. Depression disturbs sleep patterns, yet disordered sleep deepens depression. REM density often increases in depressive episodes, but its emotional calibration fails. Instead of soothing distress, dreams replay it. Treating insomnia alongside mood disorders improves recovery rates dramatically. Light therapy in the morning, darkness at night, and consistent timing reset the circadian architecture that underlies resilience. Anxiety follows a different pattern. Sleep deprivation elevates amygdala activity by up to 60% and weakens prefrontal regulation. Imaging shows stronger coupling between emotional centers and the insula, regions sensing internal states, producing hypervigilance. Restorative sleep restores the top-down control that defines calm. In essence, every night functions as free therapy. The brain rehearses safety until fear subsides. Creativity revives as well. After recovery, EEG readings display increased alpha coherence, a marker of relaxed focus. Artists and scientists often describe flashes of insight after deep rest. The phenomenon is measurable. Divergent thinking tests improve significantly following nights rich in REM. The mind, once given stillness, reorganizes knowledge into new combinations. What feels like inspiration is neuroplasticity performing maintenance. Empathy, perhaps the rarest casualty of exhaustion, returns last. Experiments where participants rate emotional expressions show that after full recovery, accuracy rises and negativity bias fades. Compassion requires energy, fatigue narrows perspective to the self. Rest reopens it. The cycle is ancient. Predators sleep to hunt better. Humans sleep to understand one another again. At the population level, public health interventions demonstrate the scale of potential change. When one Japanese manufacturing firm reduced overtime and enforced 8-hour nights, accident rates fell 40% and medical costs dropped. Schools that delayed start times by 1 hour saw higher grades and lower depression among students. Every adjustment toward natural rhythm ripples through society, improving both efficiency and well-being. The paradox is striking. Slowing down restores speed. Neuroscience continues to uncover the mechanisms behind these improvements. During recovery, genes involved in mitochondrial repair switch on. Oxidative stress markers fall. Insulin sensitivity normalizes. Inflammation markers decline within 48 hours. Even mood shifts have measurable chemistry. Serotonin and dopamine synthesis rebound, and cortisol regains its morning peak and evening trough. Homeostasis, once disturbed, rebuilds rapidly when given darkness and quiet. Sleep research also explores how to accelerate this restoration. Controlled naps of 20 to 30 minutes replenish alertness without disturbing circadian phase. Strategic exposure to natural light strengthens timing cues. Regular exercise deepens slow-wave sleep, but must end several hours before bedtime to allow cooling. Diet contributes too. Foods rich in tryptophan, magnesium, and complex carbohydrates support melatonin production. None of these interventions replace sleep. They prepare the body to receive it. Technology, once a major disruptor, can assist recovery when used wisely. Blue light filters, automated night modes, and digital curfews mimic the ancient cycle artificially. Apps that encourage mindfulness or track sleep stages may not always be accurate, but help users notice patterns. Awareness itself begins behavioral change. The goal is not to monitor every heartbeat, but to reestablish respect for rest as essential, not optional. On a philosophical level, chronic sleep loss illustrates how progress can outpace adaptation. Humanity built machines that conquered darkness, yet still carries neurons calibrated for sunset. Our inventions change faster than our genes. The lesson is humility. Biological time cannot be negotiated by technology alone. Even artificial intelligence runs on cycles: processing, cooling, rebooting. Every complex system requires pauses. The renewed interest in sleep science marks a cultural correction. What was once dismissed as laziness now commands respect as performance's foundation. Corporations design nap rooms. Athletes track recovery. Hospitals dim lights. The pendulum swings back toward rhythm. Perhaps future generations will see the 24-hour workday as a brief detour in the longer history of human rest. Yet questions remain. How much sleep is enough varies by genetics and environment, but quality may matter more than quantity. Fragmented rest from stress or screens can feel longer yet leave the body unrepaired. Measuring only duration misses texture. The balance of slow wave, REM, and transitional stages that constitute true restoration. Researchers now study sleep efficiency, the ratio of time in bed actually spent asleep. Small improvements in efficiency often yield greater benefits than extra hours gained through medication or force. As science refines understanding, the moral becomes simple: recovery is built into design. Ignoring that design has consequences. Honoring it restores order. Each night offers a natural reboot that civilization often declines. To reclaim it is to remember that productivity, creativity, and compassion all depend on the same quiet interval between dusk and dawn. And still, behind the statistics and studies, mystery endures. Why does consciousness require disappearance to renew itself? Why must awareness yield to oblivion before regaining clarity? No theory yet answers completely. The paradox keeps scientists awake, ironically studying sleep to understand waking. As they record brain waves under soft blue monitor lights, perhaps some feel the ancient rhythm beneath the hum of machines, the same rhythm that turns oceans and hearts. They know that for all our technology, every human triumph still pauses each night for maintenance. The laboratory, like the body, obeys the clock. And so the research continues, tracing invisible threads between neurons and nightfall, seeking the point where matter becomes mind again. Somewhere in that frontier lies the next revelation, a discovery waiting patiently, perhaps dreaming itself, until the world is ready to wake and notice. For centuries, progress meant conquering the dark. Factories, bulbs, and screens pushed back the night until it seemed obsolete. Yet, as sleeplessness spread, researchers began to realize that darkness is not the enemy of civilization, it is its caretaker. Around the world, scientists, architects, and even governments are quietly trying to restore what the industrial age erased, the natural rhythm of rest. The new science of chronobiology has become a global movement. In hospitals, designers study light spectra the way nutritionists study diets. Blue-rich illumination now brightens operating rooms by day and fades to amber in recovery wards by night. Nurses report calmer patients. Data confirm shorter stays. In intensive care units, where fluorescent lights once burned constantly, circadian lighting reduces delirium by nearly a third. The body recognizes the return of time. Corporate offices are beginning similar experiments. Open-plan workspaces install skylights and tunable LEDs that shift color temperature across the day, helping employees maintain focus without caffeine. Companies that adopt these systems see fewer sick days and improved concentration. Economists, once skeptical of soft factors like sleep, now calculate its monetary value. Well-rested workers make fewer mistakes and generate higher creativity. Rest is becoming a metric of productivity. Urban planners are also re-examining night. The field of dark sky design seeks to balance safety with ecology. Shielded streetlights direct beams downward instead of outward, preserving visibility while revealing stars again. Pilot programs in Scandinavia show reduced energy use and improved resident sleep quality without increases in crime. The night becomes friendly once more, its silence intact. In education, schools' test schedules aligned with adolescent biology. Teenagers naturally fall asleep later because of delayed melatonin release. Forcing early classes pits them against their own hormones. Districts that shift start times from 7:30 to 8:30 a.m. report better attendance, higher test scores, and fewer accidents among young drivers. Sleep, once seen as laziness, emerges as developmental necessity. Technology, paradoxically, may become part of the solution it once undermined. Engineers develop wearable sensors that detect circadian phase and suggest optimal bedtimes. Smart home systems adjust lighting, temperature, and sound to mimic sunset. Virtual reality relaxation programs immerse users in simulated forests or seashores, using slow breathing cues to lower heart rate. When used with intention rather than compulsion, technology can guide the nervous system back toward rhythm. Medicine is following suit through chronotherapy, timing treatment according to the body's clock. Chemotherapy, blood pressure medication, and even vaccinations show varying efficacy depending on hour of administration. By aligning dosage with circadian peaks, doctors can enhance benefit and reduce side effects. In this sense, the entire practice of medicine is rediscovering sleep's implicit wisdom. Timing is biology's hidden dimension. Neuroscientists push deeper into why rest rejuvenates consciousness itself. Using high-density EEG, they trace patterns that resemble a nightly reset of neural networks, an organized desynchronization that clears redundant connections. Artificial intelligence researchers borrow these algorithms, mimicking sleep cycles and machine learning to prevent overfitting. Even code now dreams in its own way, pausing to forget in order to learn. The cultural attitude towards sleep is changing too. Popular science books and documentaries have turned the subject into common knowledge. Phrases like sleep hygiene and circadian rhythm appear in everyday conversation. Apps remind users to put phones down. Employers host workshops on fatigue. What was once private has become public policy. Governments draft guidelines for healthy rest. the way they once did for nutrition. Airlines, hotels, and space agencies experiment with these insights on a grand scale. Long-haul pilots wear light therapy visors that synchronize internal clocks to destination time zones. Hotel rooms integrate dynamic lighting and blackout curtains controlled by circadian algorithms. On the International Space Station, where the sun rises 16 times a day, astronauts rely on carefully sequenced light to simulate Earth's day-night rhythm. Without it, cognition falters within weeks. The lesson travels back down to Earth. Darkness is not optional, even in orbit. Environmental science adds another perspective. Artificial light at night disrupts ecosystems far beyond human sleep. Insects lose navigation, birds migrate off course, sea turtle hatchlings crawl toward city glow instead of moonlit sea. Conservationists now treat light pollution as ecological contamination. Restoring darkness becomes an act of environmental repair as well as human health. In art and philosophy, the rehabilitation of night takes a subtler form. Writers and musicians rediscover stillness as creative resource. Museums host nocturnal exhibitions lit only by candlelight, inviting viewers to experience art at the slower pace of pupils dilated by darkness. Psychologists note that such events lower cortisol and foster introspection. The quiet hours, long considered empty, reveal themselves as fertile. Yet even as awareness spreads, society struggles with habit. Global commerce depends on constant availability. Digital markets never close. The next phase of evolution may be psychological, redefining success to include rest. Some economists already propose gross national well-being indexes that measure average sleep duration alongside income and education. Health ministries track national sleep trends as indicators of collective stress. A rested population, they argue, is a resilient one. These changes suggest that civilization is learning to negotiate with light rather than fight darkness. We are entering what some chronobiologists call the post-24-hour age, an era where technology manages exposure intelligently instead of indiscriminately. The goal is not to return to pre-industrial nights, but to design modern ones that respect biology. Still, the transformation will take time. Habits formed over generations do not vanish with information. The cultural belief that waking equals worth runs deep. Perhaps the greatest challenge is emotional, accepting that rest is not absence, but presence of a different kind, a state where the mind continues its work unseen. As research advances, the frontier shifts from quantity to quality, from measuring hours to understanding depth. The next discoveries may come not from laboratories alone, but from cities, schools, and homes that finally listen to the rhythms written in every heartbeat. And beyond those rhythms lies an unanswered question. If the night returns to balance, what else might follow? Creativity, empathy, maybe even a slower, wiser kind of progress. The movement to reclaim night now extends far beyond laboratories. Architects design sleep-positive buildings that breathe with the day. Apartments orient bedrooms toward sunrise. Public housing projects include communal gardens that reconnect residents to natural light. In Singapore and Copenhagen, urban planners plant trees specifically to filter glare and reduce nighttime brightness. City design becomes chronobiology in concrete. The corporate world, once proud of sleepless energy, is quietly adjusting. Major firms schedule digital Sabbaths when internal networks pause for maintenance and employees are encouraged to disconnect. Tech campuses replace fluorescent cafeterias with daylight atriums and nap pods. The change is partly pragmatic. Fatigue costs money, but also cultural. A new generation refuses to treat exhaustion as achievement. Surveys show that younger workers rank flexible hours and mental health higher than salary alone. Universities experiment as well. Medical schools now include sleep physiology in their curricula. Architecture programs teach circadian design. Students learn that light is a biological nutrient, as essential as air or food. Some campuses adopt quiet hour policies after midnight, preserving silence for study and sleep alike. What began as health advice becomes an educational philosophy. Intellect thrives when rest is protected. Public health agencies integrate sleep metrics into population studies. In Finland and South Korea, national surveys track average bedtime and exposure to nocturnal light, correlating them with rates of depression and obesity. Policymakers use the data to adjust work hour regulations and school schedules. For the first time, governments treat darkness as infrastructure. Technology continues to evolve toward cooperation. Artificial intelligence personalizes rest by learning individual patterns, detecting when the user's heart rate variability signals fatigue, and recommending downtime. Wearable devices no longer merely count steps. They map biological rhythm across seasons. Some prototypes synchronize lighting, temperature, and background sound to each user's chronotype, transforming bedrooms into adaptive ecosystems. The goal is to recreate, inside the modern home, the cues nature once provided automatically. Medical research advances in parallel. Neuroscientists explore targeted memory reactivation, playing subtle sounds during specific sleep stages to strengthen learning or extinguish fear memories. Early trials show promise for trauma recovery and skill enhancement. The technique respects the sanctity of rest while gently guiding its content, turning sleep into an ally of therapy rather than a passive state. Pharmacology explores the other frontier, molecules that mimic natural rhythms instead of overriding them. Rather than sedatives that blunt consciousness, new compounds aim to trigger physiological cascades identical to those preceding organic sleep: rising adenosine, falling histamine, cooling core temperature. The objective is not to knock the brain out, but to remind it how to let go. In parallel, cultural movements champion digital minimalism and slow living. Books, podcasts, and retreats teach the value of boredom and silence, the psychological soil in which rest grows. Families institute tech-free evenings. Communities revive old rituals, shared meals at dusk, collective prayer, walks under real stars. These customs, once dismissed as quaint, return as technology's necessary counterweight. The pandemic years accelerated this reflection. Global confinement exposed the fragility of routines and the psychological toll of endless connectivity. As people worked from home, the boundary between day and night dissolved completely. Yet within that blur, many rediscovered the pleasure of naps, slower mornings, and natural light. A cultural reset began not from policy, but from collective fatigue. Economists now speak of a rest economy. Industries built around sleep health, from smart mattresses to architecture to tourism. Sleep clinics multiply, sleep-friendly hotels, advertise decibel ratings and circadian lighting, wellness brands market weighted blankets, and melatonin diffusers. Critics warn of commercialization, but even this trend signals recognition that rest holds value. What commerce imitates, culture eventually normalizes. Artists document the shift. Photographers capture the last pockets of true darkness. Filmmakers explore insomnia as social commentary. Museums host exhibitions where visitors recline instead of walk. experiencing art horizontally, breathing in synchrony with ambient sound. The message is consistent: slowing down is not regression, it is revelation. Environmental policy intersects here too. The United Nations designates dark sky reserves, where artificial light is restricted to protect wildlife and human circadian health alike. Communities near these reserves report unexpected benefits: lower stress, improved sleep, even revived local astronomy programs inspiring children. The night becomes shared heritage once again. Education at the household level completes the loop. Parents teach children to respect bedtime, not as punishment, but as care. Pediatricians emphasize that each hour of lost sleep in youth affects growth hormone release and learning. Campaigns replace the phrase "go to bed" with "let your brain grow." Language itself shifts to celebrate rest. As these efforts converge, a new definition of progress emerges, one measured not only by speed or output, but by rhythm. Societies that value recovery may find themselves more innovative, empathetic, and sustainable. History suggests that civilizations thrive when they balance labor with reflection, noise with silence, light with dark. Perhaps the future belongs to those who remember both halves of the day. Yet challenges remain. Billions still live under relentless schedules, night shifts, and economic pressures that deny rest. For them, the promise of a well-timed world feels distant. True progress will require equity, affordable housing that blocks noise, cities with public spaces for quiet, workplaces that respect human biology as much as market demand. The science exists, the will must follow. Looking ahead, some futurists imagine a world where every device and building participates in circadian harmony. Lights dim automatically, vehicles adjust dashboard brightness, advertisements obey local dusk. Data centers power down non-essential processes at night to match renewable energy cycles. Civilization breathes again, synchronized not by clocks but by biology. Whether that vision arrives depends less on innovation than on intention. And perhaps the most profound realization is personal. Each individual holds the power to restore a fragment of night. Turning off a screen, drawing curtains, pausing thought. These small acts reconnect the nervous system to a rhythm older than humanity. In that silence, metabolism, memory, and emotion repair themselves without command. The body remembers what civilization forgot. Somewhere right now, someone closes their laptop, switches off the lamp, and steps outside. Above them, faint stars pierce the haze of a recovering sky. The air cools, breath slows, and for the first time in generations, the night feels alive again, not as absence, but as presence. Within that darkness lies the oldest form of knowledge, the understanding that to rest is to endure. And as the earth continues its patient rotation, carrying billions of sleepers beneath a single shadowed hemisphere, the rhythm that began before language quietly persists. Steady, forgiving, eternal. The future of the night has already begun. It only asks to be noticed. Morning begins long before the eyes open. Deep inside the brain, the machinery of waking starts its sequence about an hour before consciousness returns. The suprachiasmatic nucleus, the body's master clock, senses the faint rise of dawn through closed eyelids and transmits its signal to the adrenal glands. Cortisol begins to surge, body temperature climbs, and heart rate quickens. These changes prepare every organ for the shift from restoration to activity. Awakening is not a single event, but a carefully choreographed descent from cellular silence to coordinated motion. In slow-wave sleep, neurons fire in vast synchronized pulses, waves of electrical quiet followed by bursts of activity. As morning approaches, that rhythm fragments, REM sleep, with its rapid eye movements and dream imagery, dominates the final cycles. Then, as the circadian clock sends its alert signal, acetylcholine rises sharply while melatonin collapses. Brainwaves accelerate from delta to theta to alpha, marking the mind's climb toward awareness. Within seconds, a coherent self reassembles from diffused neural activity. The transition is delicate. If awakened abruptly, the cortex is only partly online. Motor systems react faster than attention, producing the fog known as sleep inertia. During these first minutes, reaction time slows, judgment falters, and short-term memory stumbles. The phenomenon explains early morning accidents and the grogginess that coffee temporarily masks. Full cognitive restoration usually requires 90 minutes, the length of a typical sleep cycle. In that time, the brain completes its chemical reset, adenosine cleared, neurotransmitters balanced, blood pressure stabilized. The hormone choreography continues beyond the brain. Cortisol peaks around half an hour after waking, fueling alertness and metabolism. Dopamine and serotonin rise in tandem, shaping motivation and mood. The gut resumes peristalsis. The liver releases stored glucose. Body temperature reaches its daily high. Evolution designed this cascade so that predators, gatherers, and modern commuters alike start the day physiologically prepared for motion. Light is the master cue. Even a few minutes of natural daylight striking the retina synchronizes circadian genes in nearly every cell. Exposure within the first hour of waking locks the body's internal clock to the environment, improving sleep quality that night. Artificial light can imitate the effect, but its spectrum and timing matter. Cool, blue-rich light enhances vigilance. Warm, amber light soothes the transition. Architects now build dawn simulation systems that brighten bedrooms gradually, guiding cortisol and temperature upward without shock. The brain reads this as sunrise. Emotionally, awakening is a return from private to public reality. During sleep, the amygdala, hippocampus, and prefrontal cortex process memories and regulate fear. As consciousness resumes, those circuits reintegrate, updating the emotional state. Some mornings bring calm, others, unexplained unease, echoes of unfinished dream work. Neuroimaging shows residual REM activity in these moments. Fragments of the night briefly overlay the real world, producing the liminal sensations of half-dreams. Within minutes, they fade as sensory input floods in. For many people, the first breath of morning carries subtle satisfaction. Oxygen levels rise, carbon dioxide falls, and the vagus nerve sends signals of readiness throughout the body. Breathing deeply upon waking, a reflex often unnoticed, stabilizes heart rhythm and blood pressure. Stretching follows instinctively. It activates proprioceptors, lubricates joints, and accelerates circulation. These ancient behaviors, yawning, stretching, orienting toward light, are evolutionary bridges between rest and movement. Cognitively, the brain reestablishes predictive models of the world it left hours before. The hippocampus compares new sensory input with memory, confirming continuity. This act of re-identification, I am still here, in this place, among these people, is so seamless we rarely feel it. Yet disturbances in this process, such as after head injury or severe sleep deprivation, reveal its complexity. Reality must be rebuilt each morning. Modern life often interrupts this natural unfolding. Alarm clocks tear through REM stages, producing abrupt surges of adrenaline. Digital screens greet the eyes before daylight, flooding them with blue wavelengths that advance the circadian phase prematurely. Breakfasts are rushed, mornings compressed into schedules. Neuroscientists studying these routines argue that the way we wake may influence the entire day's neural tone. Gentle awakenings correlate with steadier attention and lower evening cortisol. Harsh ones propagate stress. Morning rituals across cultures echo similar biology. Ablutions, prayer, meditation, or quiet tea all serve to pace the transition. Each involves rhythmic movement and controlled breathing that activate parasympathetic balance after the sympathetic spike of awakening. Where technology races, tradition remembers, the body needs a few calm minutes to catch up with the clock. On a microscopic scale, genes awaken too. Circadian transcription factors switch from nighttime repair to daytime metabolism. DNA replication halts, protein synthesis accelerates, immune cells patrol tissue boundaries. The entire organism shifts from maintenance to interaction with the world. In that sense, dawn is not merely a visual event, but a molecular one. Psychologically, awakening marks the daily restoration of agency. Dreams dissolve, choice returns. The prefrontal cortex, dormant in REM, resumes executive control, allowing planning and moral reasoning. This reinstatement defines conscious life itself, the ability to decide, to act, to imagine futures. Each morning, humanity relearns responsibility at the neuronal level. Yet awareness does not switch on uniformly. Some networks, such as those governing self-reflection and theory of mind, activate more slowly. This delay explains why early conversations feel mechanical, why empathy rises through the morning. Only after frontal parietal integration completes do social emotions fully return. In that sense, patience is biological. Compassion wakes gradually with the sun. The process of awakening also preserves learning. When the brain re-enters wakefulness, spindles of electrical activity consolidate the final transfers from hippocampus to cortex. Interrupting this stage leaves memories fragile. Students who wake abruptly from REM retain less information than those who complete the cycle naturally. Education might benefit from later schedules, not only for sleep duration, but for intact awakening. Researchers now explore the mirror image of sleep paralysis, sleep inertia paralysis, where motor control lags behind consciousness upon waking. Though rare, it demonstrates symmetry. The same mechanisms that prevent movement during dreams can persist into morning. Understanding these boundaries may eventually help treat parasomnias and clarify how the brain defines self-motion. Beyond physiology, awakening carries existential weight. Philosophers note that each morning enacts a miniature rebirth, the same person emerging anew from forgetfulness. Neuroscience lends evidence. Neural networks literally resynchronize. The autobiographical self reconstructs continuity. The ancient language of waking up to truth or enlightenment reflects this biological renewal. Consciousness must rebuild itself to see clearly. The modern world begins to recognize the value of how we wake. Workplaces experiment with sunrise rooms and gentle alarms. Schools incorporate brief morning mindfulness sessions. Hospitals time shift changes to patient circadian rhythms, reducing errors and stress. Even digital assistants now adjust notification intensity based on time of day. These adaptations echo one idea. Awakening should be gradual, not jarring. The science of awakening thus completes the cycle begun with sleep paralysis. At night, the body sleeps while the mind wakes within. At dawn, the mind wakes while remnants of sleep linger. Both states reveal the same truth. Consciousness floats between biological tides, neither fully on nor off, but continuously transforming. As the first light touches the eyelids, every heart, cell, and neuron participates in the ancient rehearsal of beginning again. The orchestra of physiology swells. Awareness rises like a tide. The world reappears, familiar yet freshly constructed. Each day is proof that restoration works, that the night did its quiet labor. And somewhere, as another dawn spreads across the planet, millions of minds cross that invisible threshold from silence to sound, from dream to decision. The miracle is not that we sleep, but that we awaken at all, remembering who we are, ready once more to learn, to move, and to dream again